He's working as a senior professional researcher at New Graphite World, Montreal, Canada. So over the past 21 years, he has conducted leading research on materials for energy storage, cathodes, anodes, supercapacitors, and solid electrolytes, and development of in situ techniques for renewable technologies. So Dr. Reddy has published more than 200 papers in various international journals. He has obtained an H index of 66 with over 16,450 citations. So these have recently placed him within the top 2% highly cited researchers in energy in 2020. So congratulations, Prof. Reddy. So Dr. Reddy is serving as an editorial advisory board member in Materials Research Bulletin and Journal of Energy Storage, as well as several open access journals. So his awards include Outstanding Science Mentorship Award, Inspiring Research Mentor Awards, 2021 Battery Materials Electrochemistry Award from the Chemistry Society of India. So he is an invited live member in ICDD USA and has given 140 talks at various conferences and workshops. Very impressive, Prof. Reddy. So now the floor is yours.
So once again, thank you, Chairman, for your kind long introduction. So maybe I'm going to put my timer on so that I'll try to finish within maybe 23 minutes so that okay. Again, thanks for the Professor Neelam Srivastava for our kind invitation, also Professor Bhattacharya and all the conference organizing committee. And also this is a nice opportunity to meet some of the well-known faces in this conference with the known people. And again, thank you very much for all the people. In fact, yesterday also attended the inauguration. It looks like very interesting. Lot of introduction is given by eminent speakers, and also some few innovative speakers already talked about some batteries. Maybe my life is a little bit easier. So although I'm trying to summarize some of the things so that within the maybe 23 minutes. So presently based in Canada, so where the Quebec is both English and French speaking colony, and also as you see that extreme climate, sometimes we go to low temperature here, the importance of electrolyte, especially people are working with electric vehicles. I think that's why solid state ionics will play an important role, especially in this region. Also sometimes to go to high temperature also. So this is my outline of a presentation. So due to time limitation, maybe I'm going to focus mainly some few cathode materials, what we did in our laboratory, and some few other examples. And at the end, if time permits, what is the importance of sustainability, especially vertical recycling, etc. So these are the small contribution in Singapore. What I'm telling, since a lot of PG students also there, what I'm mentioning that some of the examples we've been trying the lot of high school and junior college students. In fact, many students that are able to do 1 year part-time project. I think some of the publications based on the school project with various different type of programs. I think some students are able to present in the various science and engineering conference held in Singapore, as well as few other places held in especially United States and Europe and Japan, etc. So these are the small group in Singapore, as well as many people from India, and also some other places from Malaysia also. So, and also I'd like to thank my previous bosses. I think all people are familiar faces. I think Adams, and also especially I think Professor Eigenmüller at the previous world. I think if I remember, he used to mention me when he was in France at the time. First time he visited BHU, Banaras University. Almost after he's talking about almost 40 years back, first time. So that's why he told the history of your laboratory of the solid state ionics or importance of your contribution to the community. So these are my small collaboration within Singapore as well as India and other part of the world. So today I'm going to focus on some new materials we prepared in our laboratory, as well as although some interest we work with some electrolyte since our laboratory is called solid state ionics, I think, and also some other areas also we work with. So again, I think yesterday, first day, all the speakers we talked about the importance of materials for energy, environment, and healthcare. I think these are very important if you talk about the smart city. Or so overall idea is that to improve the healthy lifestyle and also to reduce the air pollution. I think that is very important. Again, the importance of materials. Not only materials. We can use it for various applications, starting from the utility and also based on the physical properties. I think in this conference has been people have been talking about different areas. I think especially energy storage is very important. If you talk about the electric vehicles or the smart grid, I think the materials will play an important role. So again, I think it is in summary cartoon. I can tell that always people are mentioning about the lithium battery, sodium battery, potassium, all type are possible. Only the promising materials. For example, if you talk about any cathode, we need a respective lithium or sodium or potassium containing compounds, and also they would expect respected voltage. I'll tell you what are good materials if it is cathode or anode for the sodium or lithium batteries are criteria that I'm going to discuss. And in terms of negative is more popular, like lithium or graphite is more popular, and silicon sometimes they want to mix the capacity into the capacity. And also other important area is that I think electrolyte. We have, I think, liquid electrolytes because of flammabilities. People are thinking about polymer electrolyte. I think again polymer electrolyte in combination with electrolyte composites. And recently, all solid-state battery, again, the importance of solid-state ionics. That's why electrolytes also will play an important role to solve the safety of our future batteries. Sorry. So these are the important different configurations. You can clearly, so as academic researchers, sometimes we focus coin cell, or sometimes we go for industry. I think we have to look for the bigger cells. I think suppose if you talk about electric vehicles, I think they put different type of 18650 cells that put it in a big type of pack. The main issue is that again you want to work with a big industry, so we have to work with electrical engineers, mechanical, or sometimes chemical engineering, and scientists start from physics, chemistry. That's why it is a very interdisciplinary research. That's why a lot of people have to concentrate in this area. So I think all people are mentioning what are the important smart materials for any battery materials. Always you're looking for high energy and power density. I'm going to explain how to calculate the high and power energy density and power density. And adapt the climate condition. That's why sometimes battery has to work with low temperature, and sometimes we go to slightly higher temperature. Again, so that's why these are limit. And long cycle life and reliability is very important. And working voltage also I'm going to discuss in the next coming slide. And high capacity. Coulombic efficiency is very important point. Always you have to get almost like 99% is good. I think impedance is also very important point, because sometimes people are talking about the so if battery is good or bad, or sometimes probably it's problem with electronic contact or some materials. I think impedance spectroscopy is very useful tool. In summary, this overall solid state ionic side is very play an important role. So it depends. We have, I think, a lot of expertise. I think maybe my future for colleagues will talk about how the AIS will be useful in terms of the electrolyte or batteries, etc. Again, the overall summary is that in the layman, you always would get lesser resistance is good during the long-term cycling. It clearly indicate that. So this is one of the useful tool. Is like less destructive analysis without opening the battery. We can monitor the health of the battery. That's very useful tool. Again, fast charging is one of the important point you to remember. The main issue is why the reason is these are solid state materials. The problem is if you do higher current rate, sometimes due to the diffusion limitations. So we sometimes you may not get higher capacity expected. That's why as always is what they call as a company or any manufacturer, they have each battery there's some limitations. That's why they fix the capacity, the current at a particular thing, so that they can get a maximum capacity. After solving, we have to look for the more safer material, low cost, and no toxicity. I think these are very important points to remember. And at the end, sustainability is very important. So I think sometimes people may ask you that what type of the important, if you talk about lithium or sodium or any type of batteries, usually we will do the raw material. I think starting from, although academic, we don't need to worry, sometimes we get small scale. If you go for large scale, any country where we need to look for some raw materials, for example, lithium, nickel, manganese, cobalt, iron, the phosphorus, they are very important materials for fabrication of electrolyte and cathode. For example, anode, the graphite is the one, so that's why we have to fabricate or graphite can get by naturally or artificially also can extract with the graphite. And also we need a copper, aluminum, and steel for cell manufacturing. And especially it is very important if you talk about the permanent magnets, we need neodymium dysprosium magnet for especially for electric motors. So whichever the country they have all this type of raw material, I think they can make the what they call, I think they can control the cost of the each, including whole vehicle cost. That's why so that's why these are all the things. That's why now we have to depend on the sometimes some raw materials we depend on each country. That's why so it's like little bit politics, whichever the country they have, they can make a lot of money. That's why sometimes some particular country they have, so like they can monopolize the market. So overall summary is that we can do mining, processing and mining, and characterization and manufacturing, and and then end use. Again, you have to recycle. That is very important. Always any material, I think is usual process, it will work. So that's why if you talk about lithium or sodium, again the cost wise sodium we can reduce further. I'm going to tell that presently all the mainly focusing on lithium maybe. So the reason is that this has a good operating voltage when compared to the sodium. Still, it depends on really what people are looking at. It depends on they're looking for the energy density or that's cost. So these are the important point. I think already people have been talking about the principle of battery. It is like shuttling of lithium between the cathode to anode, where the electron will pass to the external circuit. Whereas, for example, is the cobalt 3, there 3 plus talk. There is a simple oxidation. It means once they remove the lithium from the structure, the voltage will develop like 3 plus oxidation and reduction. These are typical cyclic voltammograms you can see for any cathode. So the same thing we can plot the voltage versus capacity. So we can see almost like 3.9 volts. So if we take iron phosphate 3.5 volts, and if it is a lithium vanadium fluorophosphate like 4.2. Always remember if it is a good voltage, so the energy density is nothing but so we need the voltage difference between the cathode minus anode multiplied by the capacity. This is the energy density of the any battery. So these are very important points you have to remember. Sometimes most commonly intercalation, de-intercalation means here the more popular in both commercial batteries, including our laptops or iPhones or including our commercial EV vehicles. So again, including cathodes, graphite is more popular, and the reason is that we don't see any much volume variation during charge-discharge cycling. Especially if you talk about tin and silicon and undergoes alloy forming alloying de-alloying mechanism. Again, here the importance of nanotechnology. We need the material should be very small size, and it is to disperse in the carbon matrix. That's why. So here the importance of nanotechnology. Although we have some other bunch of materials are there again. Although we can get high capacity. Practically, this material we cannot use for the practical application. The reason is that higher voltage hysteresis, etc. So, in summary, what are the important materials? As any young researcher wanted to start, there is always new materials to look for the low atomic weight. So, theoretically, we can calculate the capacity of any material. And as I mentioned, that the energy density is very important. High energy density means the difference in the voltage of the cell multiplied by capacity. It means that more difference between the cathode to anode is to get. And again, another important point is that both cathode and anode must not soluble with the solvent in the electrolyte. Chemically react with the solvent in the electrolyte, or if you talk about the all solid state batteries, while sintering the material, it won't react with it. Means we want a stable interface with both cathode and anode is very important. And also a very another important point to remember is good both lithium electronic and mixed ion conduction is very important, so that people are looking for the fast charging. I think these are very three minimum 4 important points you have to remember. What are the material processing as a so now we have capabilities. I think in not only laboratory, I think since industry people can produce the materials either what are the size and shape they want, almost like tons of the quantity they are able to prepare. So and with the carbon coated samples or with appropriate size that is possible. So there is thanks to chemical engineers, I think they can do very interesting things also, especially the material. That's why there is a lot of uh, advancement is happened, especially in terms of the material processing and characterization techniques. As a laboratory, I think since although we can prepare in a small scale, you can try to prepare a lot of chemical method is the advantage. You can prepare some complex oxide in a single phase you can do. And for example, if you miniaturize applications, for example, thin films, we need a physicist, you can do either by RF sputtering. Again, there is a little bit difficulties are there. If, for example, all solid state thin films, So you have to, so with a little bit interface problems as well. So with the problem with the cathode, you need to be crystalline material is very important, especially here. These are very oldest old solid state ionics problems. I am telling that, and also other disadvantages that you make all thin films. If you want to be more energy, you may not get. That's why always people do bulk materials to make a thicker electrode so that they can get high energy density. So another important point you to remember is that suppose sometimes you want even nanomaterials, sometimes you would put the product surface of the cathode or anode, some we need some carbon coating or some insulating coating. So that's why we can use some fancy technique like atomic layer deposition technique, very useful tool. And sometimes if you like as a metallurgist or for example work with all solid state batteries, we use something like hot pressing or spark plasma sintering or additive manufacturing to actually idea is that you press both the cathode and electrolyte by high pressure to make sure that we can prepare a good contact between the materials. There is a way different techniques we are going to use. So due to time limitations, in summary, I think we have to use different type of characterization techniques. Again, depending on the XRD or sometimes XA is useful to understand the chemical shift, or sometimes depending on your amorphous material, this technique will be useful. Especially for thin films, we use RBS, Rutherford basket spectroscopy is very useful tool, and the nuclear reaction analysis is also very useful tool. Afterwards, since we are a battery, again we need a material characterization, all the well-known characterization technique tools. As a batteries, we need something like galvanostat, potential start, and impedance analyzer, and a few other morphology characters. In addition to this one, I think we need some software. I think all people are familiar to use, especially Z-plot to run the impedance analysis, etc. So anyway, in summary, depends on which people can do, like including fancy with solid state NMR. Also, people can do really not only solid state ionics or conduction mechanism. We can nowadays people can do the real time with the battery. They can monitor during charge discharge, how the interface during charge discharge, how the surfaces, everything we can study. Anyway, these are the characters. I think the battery tester, impedance analyzer, either I can do something like some conductivity measurements. I think we need something like 4-probe setup. So especially since we are solid, sometimes we go to high temperature, we need something like so this type of setup is very useful, especially to not to make the conductivity cell. So now quickly I'm going to mention what are the importance of the where we are. So these are the cathodes. I think already people have been yesterday talked about. So as you can see, the main issue is that the cathode capacity is limited. Suppose we want to look for the like new material, especially this area may be more promising. Especially for anode presently, I think the most popular is the graphite. The reason is that almost we can get around 330, 340 we can get, and also advantage is a lower voltage. And sometimes we want to increase capacity, people use some silicon so that the voltage is matching with lower potential. That's the advantage. And still, as academic researcher, we have a lot of other metal oxides, nitrides, everything we can concentrate. Again, presently we don't have any other matching cathodes, so that's why these are a little bit challenges. So although as academic researcher, there are so many examples, still as the industry, they're focusing with a few, maybe 2 to 3 cathodes, maybe maximum only one or two anode materials. I think they try to focus something like some surface coating, or try to prepare the manufactured materials in a large scale, so that idea is that they can look the materials by especially to prepare in a large scale batteries. I think these are the, I think Mantiram yesterday might have talked about the importance of the layered cathodes. I think these are the well-known materials because of the capacity, the maximum capacity we can get when nickel-rich layer type compounds, and iron phosphate also. But those slightly lower capacity, still energy density, iron phosphate seems to be low cost, and also a few other things are there. So I'm going to explain the vanadium-based materials. We can write, you can use some simple carbon, what they call as carbothermal reduction method. So we use the carbon, and if you would like to prepare any metal oxide from higher oxidation to lower oxidation, to mix the carbon according to calculate about the carbon. Accordingly, we can try to prepare a very lot of oxides. Among I think we focus today. I'm going to discuss about something like a lithium vanadium fluorophosphate. So it is vanadium containing cathodes. And also, in addition to this one, we looked into some metal cluster compounds have been prepared. And also, this technique is very useful. People are looking to prepare some composites or sometimes people want to use some graphene, etc. What they call reduced graphene oxide you can do. Either or you want to prepare nitrites, this technique is very useful. Either you can purge with argon or ammonia gas, or anyway, whatever the way you want, you can do. So the overall summary is that with a simple like the tube furnace, you can do the interesting things. So here vanadium fluorophosphate. So here vanadium is in 3 plus to 4 plus oxidation state is expected, and we try to prepare the samples. And XR ratios, it is almost like triclinic type structures. So these are the typical way you can fabricate. I think all people use the binder and the conducting carbon mixed together. Finally coat the and the copper or aluminum foil depending on the cathode or anode, and roll it. Finally, your cell is make a button cell. You can try to do it. These are all things you can do it in lab scale. As an industry, so the kilograms of quantity they can do. Mixing, everything is automated. So only thing we need a lot of money, and also we need large scale manufacturing facilities, etc. We need. Overall, in summary, as a bottom cap, this usually we can do. So either your electrode coated on the materials and then electrolyte and stuff. Usually they use liquid electrolyte. Advantage is that wetting the electrolyte is easier. Sometimes lithium, so that way your life is simple. Sometimes you do with the solid state or solid electrolyte, conduct maybe a little bit issue. That's why we need a different type of application methods is needed. That's why. So most commonly, if you do look for any material, usually they do with the liquid electrolyte and they can study the performance. So usually, so nearly almost like 4.2 volts we can get by using this vanadium fluorophosphate if you compare to your other three cathodes. So in summary, anyway, it is also reasonably good cycling stability. In summary, always you have to look for the good energy density, means like we need the more difference between the charge and the discharge is needed. This is very important for the practical applications. Anyway, we can do either you can do XE2 or some impedance spectroscopy just to see with cycle number. And with our expertise, we can do, since we are physicists, or sometimes we can understand what type of, for example, surface film or charge transfer or bulk, depending on the system or phase transformation, etc. we can study. So in summary, so good high energy density, you have to look for the higher charge potential. I think that is very important. So that will determine the energy density of the future batteries. So some of the new novel anode materials, vanadium-based systems have been reported for the first time. So these are almost like these like 3.5 volt versus 4.1 volt cathode. So, and also we try to study something lithium, sodium. This is one example with the potassium. So our experience, potassium's mobility is a little bit lower when compared to lithium. Then second one is the sodium, because as you know the tiny radius vary depending on the like lithium, sodium, potassium. So another example is lithium vanadium fluorophosphate is early reported with our group, followed by I think recently, I think after 2012, after work, they work including Mantiram, including good enough, they've been extensively work on this system. I think some of the people have been some few patents from the US national labs also based on this particular system. So due to time limitations, I'm going to skip. So overall summary is that we have to get to nearly 4 or 4.1 volts, and good reversibility is very important for the practical applications. So people may ask, well, what about the same material if you talk with the sodium, lithium versus sodium? So I think these are the important points. So quickly I'll show that almost like nearly 4.2 volt versus lithium, for example, 3.5 volt hour. So although we can get lower energy density, practically in terms of cost, I think sodium seems to be almost 20% of the cost we can reduce with replaced by lithium by sodium. Another area is organic. The problem is this, although we can get some capacity, voltage, energy density wise low, because what the main issue is that we don't get compared to inorganic oxide, the capacity, what they call as lower charge discharge potentials. I think there is a little bit drawback. So I think regarding anodes, I think people are talking about the graphite is more popular. If you talk about the phyllate graphene or graphene type, although this material may not be useful because of the higher ICL, I think this may not be promising. So practically still the more interesting material is graphite. Why? Because we can get a lower discharge charge potential at lower voltage. So I think I'm going to, so almost 23 minutes, quickly I'll go through. So especially some of the anodes, a lot of tin-based oxides also we've been looking into the system. Again, some lot of challenges also there, although irreversible capacity, the first cycle is a little bit challenging to improve this one. Or here, a lot of the oxides people have been looking into the system. The main challenge is that how to reduce the voltage hysteresis is a big issue for this type of the method. That's why we cannot use this particular material for the commercial applications. So anyway, similarly with the nitrides, again, the 3 lithium can be reacted. The problem is the capacity reduction, like what they call as voltage hysteresis. Since my time is going up, and again we can do some other things, so I'm going to skip the details about the thermal stability. So what I'm telling that in situ technique is also very useful tools. For example, you want to see real time doing charge discharge things. So the reason why I'm mentioning that there is a safety limit, don't exceed the limit. So at least, for example, so try to stop according to whatever the fabricator they mentioned. So if you exceed the limit, sometimes it may catch fire, react with the electrolyte. Again, we can do some other fancy technique in solid state or X-ray absorption, etc. I think finally my time is up, and then so materials, whatever the research we do, so at the end we have to do some recycling. So because it leads to a lot of environmental issues, that's why it's almost like 900 million, almost 11 million metric tons of the spent batteries in discarded to 2030. In the sense that there is a lot of effort, especially for the mining and metallurgists. So especially, this technology already known. The only issue is the cost, and then that's why people are. So there are some additional cost is going to happening. So that's why there is another group of people also they're concentrating on the recycling technology. Again, these are the pre-treat. This is the way people can do. In summary, I think I talked so many materials. Among them, popular is only NMC or two, something like 2 to 3 cathodes are promising. And still, I think always research wants to go. I think we need something like novel materials, but especially in terms of high energy density. Again, in terms of I didn't discuss about the electrolyte part. Is in fact, although we climb some the electrolyte, or sometimes the problem is polymer electrolytes. I think how to any polymer electrolyte we have work at room temperature, or solid electrolytes also we work with higher current rate is a real challenging. I think there is interesting things going on. Still, I think the cooperation between scientists and engineers are needed for the large scale application. Okay, thank you very much. Okay, maybe I can take some questions.
All right, thank you, Prof. Reddy, for the very informative sharing. So due to the time constraint, we can take 1 or 2 questions from the floor. So students, please take your opportunities. Any questions from the floor, please?
Or maybe you can send me my email also is okay, so that later.
Yeah, but before that, Prof. Reddy, can I have a question? Can I ask the question here? Just one will do. Okay, thank you very much. Prof, when we are talking about the cycling of the this kind of electrode materials, both anode or cathode, either one. So what is the threshold for the cycling, so that can tell us that these materials has the potential for the commercialization?
Okay, so commercialization means, as you know, that presently we have NMC with a 240 there. Cycling is that I told you that voltage maybe 4.2 or 4.3 is really, that is the way I told the energy density means like whatever the way you do, or sometimes in the capacity. So to get higher voltage as well as the capacity. Sometimes nowadays, although we can, for example, I didn't discuss about some anode material, a lot of metal oxides. Although we can get higher capacity, do some discharge. Practically it may not be useful because we cannot replace the graphite, because for anodes you have to get a lower. This is a little bit difficult. That's why, although so many materials people are looking, the only few materials are promising. Still, in terms of the cathode side, is a little bit limitation. We cannot able to reach the maximum capacity, but there's a little bit challenge still. That's why. So in order to reduce the weight of the batteries, I think we need higher energy density. That's why there is. So no other option still based on the existing material. People are looking some coating to improve the performance, and then studying in future. I think people can do some earth-shaking research. We may get another Nobel Prize. We don't know. They're expecting. Thank you.
Yeah, Prof. Reddy, can I one more question from me? Sorry.
Yeah.
Prof, beside all this voltage, right? What about the cycling? Is there any threshold?
Okay, cycling is, I think people are, the industry again is a little bit tricky, because although academic research do 50 cycles, that is not really practically true. If you go for industry, they do fabrication is different, then they can go monitor almost like years together too. Again, it depends on which electrolyte they're putting. The limited secrets are there. So that's why each company, each fabrication, their own electrolyte, their own formulation. So that's why some trade secrets are there. They're all mainly depends on how the electrolyte, how packaging, that is a little bit challenging. That's why sometimes what we are talking about, the coin cell story is different when you go for real.
Yeah, it's true. It's true. Okay. Thank you very much, Prof. Reddy, for being with us today. Thank you so much. So without further ado, I have Prof. David with us already. Prof, how are you? So next, we will have our plenary session with Prof. David. So allows me to read to you some brief biodata of Prof. David. Yeah. Okay, so Prof. David obtained his PhD in 2009 in materials chemistry, and he is currently the professor in the Department of Chemistry at the University of Waterloo. He worked at the University of California as an NSERC postdoctoral fellow from 2010 to 2012. So Prof. David has several awards and honors to his name. He has been recognized as the highly cited researcher, okay, from Web of Science for 3 consecutive years, 2019, 2020, and 2021. So he has been awarded with the prestigious Battery 500 Seedling Award for the year 2017 to 2019, National Science Foundation Career Award, ACS PRF Doctoral New Investigator Award, Innovation Challenge Award, Natural Sciences and Engineering Research Council of Canada in 2010. He is the Associate Editor of Carbon Energy since 2019, guest editor in Chem, which is a journal of chemistry and sustainability, energy and materials, and Journal of Solid State Science and Technology. He is also the editorial board member of eScience and Scientific Reports. So Prof. David is a referee for several journals, including Science, Nature, Nature Nanotech, Journal of the American Chemistry Society, and so on. He has also been the organizer for symposiums in MRS meeting, ECS meeting, and ACS meeting. He has authored 145 articles in peer-reviewed journals with 27,000 citations and an H index of 68. Very impressive, Prof. I hand over the floor to you. The floor is yours now, Prof.
Thank you so much, Professor Tan, for the kind introduction. And thank you for the invitation as well. It's a great pleasure to give a talk remotely. I think during the pandemic, this is something we can still have, a conference virtually. Anyway, so the topic today I want to share is sort of like a journey of 10 years I had gone through at Oregon State. And I'm going to introduce some snapshot of what we do and what we have done at Oregon State for the last 10 years in terms of trying different charge carriers for electrochemical reactions. Anyway, so let's talk about, sort of like a bigger picture. What is the storage battery? So how is it different from power battery? So from the talk Dr. Reddy just gave, I think you probably have a good clue about power batteries, lithium-ion batteries. And for lithium-ion batteries, the goal is really to increase the energy density and also have the cycle life, right? So, but for storage batteries, it's different. It's all about the cost. So we're gonna have the freedom that we don't have to worry on every day too much about the energy density anymore. So that actually provides us the leeway to design different electrochemical reactions from a reaction point of view, instead of thinking as a material scientist. So because I was trained as a chemist, it's actually my intuition to think about electrochemistry or batteries as a box for reactions. Anyway, so currently all these technologies, lithium ion all the way to nickel metal hydride, they cannot meet the market for storage. So they have all their own issues. I won't actually talk about them due to the time limit. So today I want to actually mention, as I said, snapshots of several charge carriers and their applications. So I want to talk about sodium, potassium. It's kind of ambitious, but bear with me. Ammonium, proton, copper, iron, fluoride, iodide. So let's get started. So the first slide I want to share is, sodium-ion batteries become now quite, I would say, I won't use the word of popular, but it is getting a lot of attention right now after CATL announced their commercialization plan for sodium-ion batteries. In 2012, when I started my group, my first project was to study this anode for sodium-ion batteries. That was my interest for a few years. I want to condense over the years what I have learned on hard carbon. I don't have time to explain, how I arrived at the conclusion on hard carbon. So the design principle of hard carbon, just one sentence I want to share with you, which is a low surface area material to minimize the Scatter reactions on the surface of the electrode between the electrolyte and the electrode. And you want to have expanded carbon turbostratic structure so that you can promote the sodium ion storage for the plateau. You want to have more benign, low energy defects of the carbon so that you can promote the slope for the profile for the storage of sodium ions. So we all know that probably graphite doesn't do the job for sodium ion storage. It's not just the graphite fault. It's the combination of the binding energy between sodium ions and graphene layers, and also a relatively large cohesive energy of sodium metal. Is this difference between this term and that term, the metal term and the carbon sodium binding energy, that term, the difference of those two terms is not negative. So you don't have the voltage of the cell, half cell, being positive, right? So I'm just using enthalpy here to represent the free energy change because of the entropy change, entropic change is pretty minimal. All right, that's the first insight I hope to share. So this is a hard carbon. We also studied soft carbon, and the conclusion is if you want to commercialize soft sodium-ion batteries, I think a hard carbon from abundant precursors will be the way to go. So how to design that? The design principle, as hypothesized right here, and if you combine that with the precursors you can find with abundancy and a low cost, I think that's probably the way to go. So the second snapshot is potassium ion storage. Back in 2014 or 15, we studied sodium-ion batteries for a few years, maybe 3 or 4 years already. I had this uncertainty. I don't feel comfortable continuing working on sodium-ion batteries because I was not convinced that sodium-ion batteries will solve the storage problem. Because sodium-ion batteries, still non-aqueous. It can still explode. I just don't trust anything that is non-aqueous, containing flammable solvent, not explosive. There is even slight possibility, which is unacceptable. So then, actually, before I realized to move on to aqueous, my conclusion was, why not studying potassium? Although potassium is a lot bigger, but probably is going to provide something that sodium cannot afford. For example, to have the ions stored in graphite, right? So we tried it. No, everybody says it's impossible. You cannot put potassium ions in graphite. But it's a simple experiment. We did it anyways. So it works pretty well with the staging phenomenon. You have the graphite, stage 3, stage 2, and stage 1. So, and then reversibly, you can remove potassium ions from stage 1, 2, 3, and to graphite. It's quite reversible.
The downside of graphite is the cycling performance is not that good because the volume change is 61%, which is not trivial, which is pretty significant, and it's going to cause the battery to fade. And then we start, we have done a lot of work on sodium ion storage in hard carbon and soft carbon, of course. We just translate what we have learned to potassium ion storage. It turns out that it's pretty stable. So potassium, if we want to really commercialize potassium ion batteries, the advantage actually is graphite. Because graphite is still abundant, it's actually cheaper than hard carbon in many ways. And if you can use graphite as the anode for potassium ion batteries, I think this type of battery has a future. Now, how to solve that fading problem? I think it's doable. 61% is not the end of the world. It's doable. But you have to introduce some kind of hard carbon or some other carbon as an interrupter or binder to prevent the overall volumetric change. Anyway, so that's for potassium. Recently, we had a study as a collaboration with Dr. Jun Liu from University of Washington in Seattle. We studied a fuel cell. So here I want to share another insight. We have learned potassium ion storage in Prussian blue cathode is very, very reversible. But how do you know it? You cannot use potassium metal as the counter electrode. It won't work because potassium metal as a counter electrode will mess up everything. It will react with electrolyte. You will never know the true cycling life of the cathode. So we have to use something else. And here we used activated carbon. So now we know for the first time, Prussian blue as the cathode to store potassium ions is extremely reversible. All right, that's for potassium. And then, we had some fun with, again, with big ions like potassium, and we finally decided to move to aqueous. That's my recent interest. We have spent roughly 5 years, or maybe a little bit more than 5 years, 6 years on only aqueous batteries, pretty much. Because I believe aqueous is safer, right? That's the premise. So, with similar sizes, with similar ion radii, ammonia is 1.41 picometer angstroms, and potassium is 1.36. So we want to know whether ammonium will be stored as a charge carrier. And you can use Prussian blue, Prussian white. These are the same thing. It's just, this one is more reduced format of Prussian blue analog. And we found that big ammonium ion fits Prussian blue better than smaller, slightly smaller potassium and a lot more smaller sodium. So big ions fit big voids better. So why small ions won't be fitting? Because small ions in aqueous electrolyte, they bring in solvation with them. Small ions are solvated, in this case, hydrated. They bring in water molecules. The water molecules interact with the host, which is destructive. So that's another thing I want to share. So something interesting going on afterwards, and we found, ammonium ion. Ammonium is different from potassium. Ammonium is molecular, is non-metal. It has a lot of protons. So, and then it comes like, if you have protons, what about hydrogen bonding? What about hydrogen bonding? So it's not going to be pure ionic bonding anymore, because if we insert ammonia into metal oxide, the space is so crowded that the proton or hydrogen atoms of ammonia will have no other choice but to interact with oxygen atoms of metal oxide. When they interact, because they are so close, they have to form extremely strong hydrogen bonding. So that's the hypothesis, and we hope to see some kind of flavors derived from the hydrogen bonding. And it turns out that is pretty significant. If you look at the performance of the same V2, same V2O5 bilayered structure to store potassium ion, it's typical. You call it battery performance with the peak separation, and then for ammonium ion, you have this vertically aligned, and we call that kinetically reversible behavior. And this is something we call it diffusion-free, non-diffusion controlled. I apologize, non-diffusion controlled. Okay, so all we call it, capacitive. And then we realized something afterwards. So this is the typical explanation. You can find such behavior in a well-known Dr. Bott's book, right? So we find something with ammonium ion inserted. You have this vanadium oxygen vibration completely transformed. It's split into two peaks for each of them. These two vibrations, these two types. If you insert potassium ions, you don't have that phenomenon. So the peaks won't split. So the splitting of the peaks is telling about directional bond. So you have directional bond of the charge carrier with the host, and directional bond is typically covalent interaction. And potassium obviously cannot do that. Potassium is ionic. So and then we had this conjecture afterwards. There must be some correlation, or there would be some correlation between the donor-acceptor type of bond and the capacitive, pseudo-capacitive behavior of the ion electrode whole system. There must be a sweet spot. If it's completely covalent, you won't have redox behaviors. If it's completely ionic, for potassium, we don't have capacitive behavior. So, and here we also observed charge transfer. That's something new. The charge transfer happens to the negative charges, the electrons, are shared by V2O5 with ammonium ion. So ammonium ion is partially reduced, right? So ammonium ion now is not +1. This is typical for lithium ion in graphite. I think people have talked about this for decades, but that's kind of vague. But this ammonium molecular ion, you have the LUMO to do it. You have the LUMO orbitals, right, to host charges. So it's a little bit different from lithium case in graphite. Anyway, so let's move on. Let's move on to the next non-metal ion. So we were looking at hydronium for some time, and then we were thinking, well, if you spend time on hydronium, why not just proton? Just look at proton. That's a lot better. Proton is the smallest and the lightest ion ever, right? So if we want to conduct proton, and then suddenly we realized, oh wow, we should use Gross's mechanism for storage of protons. In 1805, von Grosses published his work in Rome, which was translated to French in 1806, which is this paper. He introduced the diffusion-free proton conduction. So when you have a proton coming to this water chain, this proton will combine with this water molecule, and this is going to form a hydrogen bonding first, and later this hydrogen bond will be converted into a covalent bond. And this originally covalent bonding will be weakened to a hydrogen bonding, and then this hydrogen will switch its allegiance from this water to the next, right? So basically, this hydrogen is no longer associated with the original water, becomes a part of the next water. So with this vibration type of behavior, you have the structure diffusion, the charge transfer is done. The charge transfer is not done by the conducting of protons, but by the conducting of the charges of protons, right? So that's the difference. All right, if this is not just unique for protons, it could be other, media, iodine, lithium in solid state electrolyte. You can also have those phenomena. But for water and proton, is the most obvious choice for us back then. So we need to have water to have the Gross's mechanism. So then we tried to install a network of water molecules inside the solid of the electrode. And what we use is very obvious, actually, back then, Prussian blue, because we studied Prussian blue for a long time. And we just had to make Prussian blue defective. when we remove parts of the nexus or the islands of the structure, we can actually have a lot of defects and to host water molecules as lattice water molecules. And these lattice water molecules, if they're close enough and they start to talk by hydrogen bonding, they're going to have a hydrogen bonding network. And with that, we will have the Gross's mechanism, right? So that's the hypothesis. And it turns out that it's pretty impressive in terms of the kinetic reversibility. The kinetic reversibility for proton. The same electrode, it doesn't have that behavior for sodium, for potassium, for ammonia. But for proton, you have the kinetic reversibility. That's quite interesting. And the rate, the loading, active mass loading of this electrode is around 2 to 3 milligrams per square centimeter. Yeah, so it's not too light, I would say. We also tried, heavier electrode. It's not really high quality electrode the industry would make, but we still have very good rate capability. So I think the proton batteries will be a serious challenger in the future to lead acid batteries. Yeah, and that's very possible. So it is actually becomes interesting to observe the history of pseudocapacitance. The first generation introduced by Conway in 1960s, 70s. We were talking about the surface behavior, and nanostructures, for example. And then later in the early 2000s and 2000 maybe till 2015, and Professor Proton introduced the intercalation pseudocapacitance. You don't have the structural change. The structure is really rigid. It doesn't expand or shrink for the ion storage, and they call that intercalation pseudocapacitance. And I think we should probably give a title for Gross's conductions, Gross's conduction as a pseudocapacitance type. For this case, we don't even need the diffusion of ions into the structure. So that's the fundamental difference. All right, so now we have talked about some non-metal ions. Let's briefly talk about transition metal charge carriers. So the first example I want to introduce is copper. So this is the galvanostatic charge discharge profiles for sulfur electrode. This is probably commonly known. This is for lithium sulfur, right? Lithium sulfur battery has received a lot of attention. I studied that during my PhD time. And then this is manganese, and this is copper. This is copper. So the interesting thing here is the potential of copper storage by sulfur is a lot higher. It's a lot higher. And the capacity is seemingly higher, but I don't have the charge carriers considered as the mass of the entire system. So it's not fair. It's not fair. But this is better. This is more fair. Okay. And we have charge carriers considered for the mass of the electrode. Of course, copper is extremely heavy. The capacity is lower, but the potential is a lot higher. So the overall, the energy from, if we don't consider anode for this time, we just consider the energy of the cathode, and the copper sulfur system is more energetic than the lithium sulfur system. And these are not theoretical. These are all measured. These are all experimental results. So 2 more features I want to highlight. Extremely small, the minuscule polarization for copper. Almost no polarization for copper. For lithium, you do. The reason for this is the semiconductor nature of the cuprous sulfide and the cupric sulfide. It's not just about electronic conductivity. Cuprous sulfide or cupric sulfide, they're also ionic conductor. So they're both ionic and electronic conductor. That's why the polarization is extremely small. For lithium sulfide, it's not a conductor for any conductivity, right? We know it is insulating for ions and electrons. So third feature I want to highlight is we don't have polysulfide shuttle mechanism for copper. And for lithium is well known, you have that. And the reason for that is for copper reduction and oxidation with sulfur, copper binds sulfur too strongly. It doesn't give a chance for sulfur to evolve into polysulfide. And this similar phenomenon takes place for iron, ferrous iron as well. So we don't have polysulfide shuttle mechanism. So of course, iron battery, recently, we have done several studies on iron battery with iron metal as the anode and some host as the cathode. But I think the real challenge for this type of battery, which was first invented by Edison or by a Swedish scientist, but 100 years ago, true challenge is on the anode side. All right, I don't have time to talk about that, but this phase diagram could be useful if you are interested in the field. So I want to summarize what I have probably shared today, very fast. Actually, biology, I took that out. So for binding energy is, the overall calculation between binding energy and the cohesive energy or the metallic bond is something you need to think about probably to understand why sodium ions can be stored with this or that kind of carbon. And it's not about a size. The size doesn't matter sometimes. It's about energy. It's energy-driven process. So even bigger potassium ions can be stored by graphite, right? Despite being much bigger. Ammonium ion actually is quite interesting. It's non-metal. It's molecular. It has a lot of flavors to form chemical bonding in covalency and strong hydrogen bonding. Sometimes you could have pseudo capacitance simply just to study this material, this ion. But you have to worry about the hydrogen bonding flavors. If you use metal oxide, probably can be very optimistic that you probably will see some kind of pseudo capacitance. Protons, I think is very promising technology because it has the potential to use gross conduction. But if you have too much lattice water, it's gonna make your electrode quite heavy, right? That's a caveat. So I won't talk about hydrogen. That's another interesting system. But I think if you even increase the size of the charge carrier, the electrochemical cells are no longer batteries. They are reactors to synthesize new materials or new molecules. So transition metal ions, they bind with their host pretty strongly. That could be used for different applications. The last one is, I didn't probably talk about this too much. Copper 2+, ammonium, hydrogen, all of these ions, they are redox active. They can be reduced. These ions are electrode by themselves. It's like a plating reaction, right, to some extent. All right, so let me move on to ion ions. So ion ions. Before I talk about ion ions, I wanna talk about the four basic battery operation principles. So the operating principles for all these four different configurations are built upon very simple rule. The rule is the electrodes need to stay neutral during the redox reactions. For example, if you have anode during discharge, it's going to lose electrons. To stay neutral, it has two ways to do it. One is to lose cations. The other is to gain anions. Conversely, for cathode, during discharge, well, when I say cathode here, I mean positive electrode, right? And during discharge, it's going to gain electrons, right? Gain electrons, and then simultaneously you want to gain cations or you lose anions to stay neutral, right? So now we have these four scenarios, and we just connect them. We just connect them, very simple. You connect those two top boxes, you're gonna have charged the cation rocking chair battery. So lithium-ion, sodium-ion, potassium-ion batteries, all kinds of metal-ion batteries, they fit this this box or this category of cation rocking chair battery. And now the bottom two boxes, you connect them as anion rocking chair battery. The recent papers by a German professor, Fichtner, chloride batteries, fluoride batteries. There are quite a few papers on that front. Now, if you connect in diagonal directions, you're going to have dual ion batteries and the reverse dual ion batteries. So, so let's talk a little bit about dual ion batteries today. So dual ion batteries were initially invented as something called a dual graphite batteries, and both cathode and anode are graphite. So during discharge, you're going to have ions moving towards the two electrodes respectively, anions to the cathode, cations to the anode, and during discharge, they both come back to the electrolyte. So it works like a playing accordion. So we gave that a accordion battery name in one of the papers. So initially it was pretty challenging to use graphite to store anions because graphite is kind of compact and the storage potential is relatively high. It causes the decomposition of the solvent of a non-aqueous electrolyte, and people started to have to, there has been a lot of work by Professor Martin Winter in Germany to use anionic liquid, right, to make sure that the cathode is analytically stable and it's going to survive the reactions. So I won't talk a lot about that direction. What I will highlight is we found that if you use, for example, coronium, it's a molecular solid of this interesting molecule. We don't have that high potential problem. The potential goes down to 4 volt. Right? That's a benign volt potential for a lot of organic solvent. And the potential, the capacity is extremely low. That's true. But there is something going on with this low potential. So back then, we had some understanding on a sodium ion storage in graphite, in hard carbon with defect, and we started to think, can we use this, enthalpy change to explain why the potential is lower for coronium? So it may have to do with the binding energy of the anion with the host. And what I can think of right now, or for some time, is the binding energy of the anion with the carbon host. In this case, it's not pure carbon; we have hydrogen here. This is less negative. This is less negative for molecular solid. And then the delta H is less negative as well, and that causes the voltage to be less positive. So to test this hypothesis with experiment, we explored some other molecular solid which has even lower density, so that we can minimize or we can lower the binding energy between the anions and the host. So this is the paralleling. You just take these 2 rings away, you're gonna have that. And if you take 3 rings away, you're gonna have the triphenyline. Right? And for triphenyline is kind of dramatic. So the potential from coronium is 4 volt going to 3.7. For paralleling, it went all the way down to 2.5 roughly for triphenyline. So this is not just the density thing, maybe. I think if we want to push forward and to have more fundamental studies, it has to do with, I believe, the homolumo structures of the molecules as well. So I'm actually at maybe 29 minutes, right? All right, so I'll push forward. So another factor that will affect the voltage is the activity of ions. If the ions is more concentrated, the potential will go down. This is the case for the concentrated zinc chloride. And with concentrated zinc chloride, you don't have actually free chloride. Most ions are the tetrachlorozincate, is this ion. So we have this ion stored in ferrocene. That's the ion. That's the anode. So with that actually observation, we saw, okay, you have this almost like a super coconite, right? Super coconite. So what about super halide? So we studied super halide. One of them is magnesium trichloride. And again, we design different electrolyte. And here 9 means non-molality magnesium chloride. 10 means 10 molality choline chloride. So, and then we increased the concentration of choline chloride, and we started to have this redox behavior. We have a lot of chloride. Magnesium, we have no choice but to form this superhalide. And when this superhalide is formed, it's getting concentrated, and the insertion potential will go down for its insertion in graphite. And also when the electrolyte is concentrated, water will be less subject to oxidation reaction, or water oxygen evolution reaction, OER. So we do have some charge discharge behavior for this ion storage in graphite, although the Coulomb efficiency is not that good. All right, we have another chloride insertion. So to decrease the anion size is critical. That's one direction we have been pushing. So superhalide are okay, but they're kind of bulky and heavy. So just simple halide is even better, but it has been very challenging to store simple halide in compact organic structures or graphite. So typically from aqueous electrolyte, so everything here is aqueous electrolyte, by the way. So we have done it. We have a good capacity for chloride in Mn304. That was supported by the evidence of electrochemical quartz crystal microbalance studies. All right, so for ion storage, I think the best way is not to store ions. The best way is to plate ions into neutral mass. It's like for lithium. Lithium insertion electrode will never have a capacity better than lithium metal, right? So it's kind of interesting to see people report capacity of silicon higher than lithium metal. That's impossible. That's impossible. So lithium metal is a plating electrode, and we hope to see whether we can plate halide. So, and I want to actually probably talk this paper first. This is Chun-Sung Wang's paper, Dr. Chun-Sung Wang in the University of Maryland. He did it with plating of chlorine. But chlorine is a gas; you cannot plate it. So the plated molecules are actually as interhalogen actually stored in graphite. Right. So we had iodine in this case. We want to plate iodine, but if you have iodide in the electrolyte, you cannot plate iodine. Why? Because iodide will react with iodine to form triiodide. It's going to dissolve away. It's going to dissolve. So the reason to the solution to solve that is we need to remove iodide from the electrolyte. We need to hide the iodide in somewhere else. And we have learned that in this system, we don't have free chloride. So if we have iodide added into this system, probably we will not have free iodide either. That's the case actually. If you add potassium iodide into a concentrated zinc chloride electrolyte, you don't have free iodide. It's mostly zinc iodide complex ions, right? So we have an interesting system, which is a dual plating battery. The cathode is iodine plated, and anode is zinc plated. All right, and we pushed further. We also want to involve chlorine because chlorine is lighter, and then a new electrolyte is designed. We have zinc chloride concentrated. Choline chloride is extremely concentrated. I won't even call it water in salt. There's not much water. This is just eutectic solvent or deep eutectic solvent, right? We also have iodine. So now here, the reaction is following these three steps. First, iodide oxidized into iodine, and iodine oxidized to combine chloride, and then this hydrogen ion is inserted in graphite. So this reaction is going to be sensitive to it's going to depend on the surface area. You probably can see that because you need a plating first. So we worked on an extremely high surface area material. The capacity is extremely high. It's 1100 milliampere hours per gram. This is probably the highest capacity electrode for anion storage. All right, I think that's about it. So I want to share here is the anion insertion. Potential is really depending on the lattice energy and also the the activity, and a little bit information about superhalide. For anion storage, probably plating just as metal is better than insertion because you don't need a host, right? You don't need a host. It's much lighter. And if you want to really plate ladder halide, you probably need the inter hydrogen bond so that you can stabilize the ladder halide. All right, that's my collaborators, all my funding agencies and the collaborators, and these are the students who have involved in the research here. And some of them are PhD students from my own group, and some of them were visiting students, and they have done all the work. I didn't do any of these experimentally. And with this, thank you for your attention.
All right, thank you very much, Prof. David. I can allow one question from the floor. Yeah, Prof. Nilam, yes.
Well, thank you for the invitation.
Okay, thanks again, Prof. David, for being with us. Thank you so much. Okay, so without further ado, I would like to invite our third speaker of this session. We have with us Prof. Anshuman Dalvi. You are with us now? Okay, thank you very much. So please allow me to read a very short biodata of Prof. Dalvi. Yeah. So he is currently a professor in BITS Pilani. So Prof. Dalvi did his MSc in physics in 1997 from the School of Physics DAVV Indore. He did his PhD from IIT Kanpur in 2004 under the guidance of Professor K. Shahi. His research interest lies in fundamental aspects of ionic transport in solids, particularly glasses, glass ceramics, polymers, and ionic liquid confined energy materials. He is also interested in the application of fast ionic solid electrolytes to energy storage devices, particularly lithium-ion and sodium-ion-based all solid-state supercapacitors and batteries. He has been serving BITS Pilani for almost 18 years. His lab at BITS Pilani, India is fully equipped with fabrication and characterization facility for all solid-state supercapacitors. The lab is also equipped with fundamental sophisticated materials characterization facilities. He has been an INSA Fellow for International Bilateral Program to work in Warsaw University of Technology, Poland in 2014. He has about 70 indexed international publications, out of which 40 reputed journals. He headed the physics department of BITS Pilani for one full term and currently serves as Associate Dean for Faculty Affairs. Okay, the floor is yours now, Prof. Delvi.
Thank you, Professor Vinny. Is my presentation visible? Just want to confirm.
Yes, yes.
Yes, thank you very much. Thank you very much, the organizers, Professor Srivastava, Professor Bhattacharya, for giving me this opportunity to speak on some simple results which we have obtained in the laboratory by my PhD students. And I thought that these are very interesting and this is the right time to share in this conference particularly. So it's about solid polymer electrolytes dispersed with Nasicon structured nanocrystallites for all solid state supercapacitor applications. We have been listening about the batteries since yesterday, and there was, I think, one lecture on supercapacitors as well. But we are, as a scientific community, looking for the all solid state batteries. So at the same time now, it's the right time that we should look for all solid state supercapacitors also. With that idea, we initiated this fundamental work towards the devices, towards the understanding of the physics behind the processes and the devices. So, well, we all belong to a community, solid state ionic community, and in this community, we would like to talk about the all solid state, that means liquid free devices particularly. There should not be any liquid, and if that is the case, then there are various issues we have to deal with: the electrolyte part, the electrode part, the interfaces, and various interesting work has been happening for last 30-40 years, in fact. So here the all solid state supercapacitors can be another interesting addition to this work, on which there are few groups working, and we are also one of them. And I just would like to talk about something relevant to these things. I'm a man of ceramics, basically. I have been working on fundamental aspects of ceramics, glasses, glass ceramics, various superionic conductors which were developed and their physics and the electrical transport processes. So we all are well aware about the ceramic fast ionic solids, right from Li3N to nasicons to garnets. And on the other hand, we are also aware of the solid polymer electrolytes, in which I am talking about all solid polymer electrolytes. That means not the gel part, but the salt which is dispersed inside the polymers. There has been a work on these two in these two directions, but because of the interfaces, we are not able to really materialize the device. We are not able to realize the devices actually. And therefore, there is a time that now we should fuse these two things together and try to look for some new systems which can give a better ionic conductivity and possibly better interfacial properties as well. So if you see the nasicon, I have taken nasicon for this work. One can take garnets and perovskites also. Nasicons are the super ionic solids. They have three-dimensional pathways for lithium ions to move, and they have the skeleton of this titanium octahedra TiO6 and phosphorus PO4 tetrahedra, and they are sharing the corners, so there is a lot of space inside. So we have some sites like M1, M2, and some recent studies have given M3 sites also. M3 site is occupied with only 7% of the lithium ions, and M2 site is occupied with 14% of the lithium ions, and M1 site is completely occupied by lithium ions. You cannot see the movement of lithium ions along M1, but you can see the movement along M2 and M3, and by some doping, we can use these M1's lithium ions to travel through the M2 and M3 sites, and therefore there is a huge conductivity in nasicons. A very similar process is there for the garnets also, where you have defects, and through those defects ionic motion takes place. So one talks about the ionic conduction, then inside the grain, ionic conductivity is as high as 10 to the minus 3 ohm inverse centimeter inverse in many of these materials, particularly garnets and nasicons. But when you talk about long range ionic motion, then the grain boundaries create a trouble, and grain boundaries offer a lot of impedance. High grain boundary impedance leads to the conductivity dropped by few orders of magnitude. So the total conductivity is not sufficient in that case for the purpose of the devices. On the so this this solid interface is another issue that when we see by our naked eyes, and it appears that there is a good contact, but then at the interfaces, nothing is smooth, and stability with respect to temperature, huge energy barriers are there, so ionic motion is not at all possible. Therefore, possibility is to look for the soft materials. That is also being developed in last 30 years or so. And here you talk about the solid polymer electrolytes, in which in 70s people started working on the theory behind a SPE. So the salt, when it is dispersed inside a polymer matrix like polyethylene oxide, high molecular weight polymer, then wherever the salt goes, then you create domains of amorphous regions, and when these domains are connected to each other, then the ionic motion begins. And ionic motion begins because there is a ether oxygen with which the lithium ions couple, and this coupling, that means the ion chain coupling, is considered to be, it's thought to be the real process of the electrical transport in these polymers. Now in the polymers you can see there is a flexible structure, there is a space, but the process of electrical transport is slow because this coupling is the mechanism. And if you see the Nasicon kind of materials, inside there is a three-dimensional structured array, possible pathways for the ions, but then at the grain boundaries electrical transport is hampered. So to look for combination of these two, one talks about a hybrid where we think about dispersing the Nasicons inside the polymer matrix. Long back people disperse insulating particles inside the polymer matrix to enhance the conductivity, and there could be a order of magnitude or a little more enhancement in the conductivity, but it was finally limited because of the size and shape of the insulating nanoparticle and the amount of nanoparticles also. But when you disperse these insulating, not insulating now, the superionic nanoparticles inside the polymer matrix, then these nanoparticles also provide pathways for the electrical transport because they themselves are also conducting. And polymer, if it is in low amount, then it is about ceramic in polymer. But if if the ceramic particles are in low amount, then it is about ceramic in polymer. But when you have large amount of ceramic, then it is essentially polymer that goes into the ceramic and sits between the grains of this ceramic. So this way we can make a composite which is highly conducting, as well as in which the interfacial transport becomes quite smooth. So we did a lot of work on these materials in sodium and lithium structured Nasicons, and tried to understand the mechanism of electrical transport, tried to enhance the conductivity, and also obtain a conductivity between 10 to the -3 and -4 in the solid state, in the solid polymer state. And therefore we thought that now it's time to apply them somewhere and see how interesting results one can obtain. So the very first application could be in the super capacitors. And when we talk about super capacitors, there has been a lot of experiments in the batteries of similar materials, but in case of super capacitors, this is one of the first experiment that we thought. To introduce a little bit about super capacitors, the super capacitor is like a 100-meter runner, like Usain Bolt, which delivers the power in very short amount of time. Huge current can be drawn in very small time. But then batteries is like a marathon runner, which for which the one can draw power, but slowly and for very long time. So here the power output is low in case of the battery, and the energy density is low in case of the super capacitors. So the Regon plot and all possibly it has been discussed, so I would like to skip this, and I would like to say that super capacitors are normally having 2-3 dimensions, particularly the electric double layer. Then the next one is the pseudo effect. Just in the previous little bit of that has been covered, and the combination of these two could be the hybrid supercapacitors. A little bit about introduction of supercapacitors will be useful here because looking at the undergraduate and graduate students in the conference. Whenever we dip any metal or any object inside the electrolyte, then the electrolyte will have particularly 2 layers surrounding it. The electrode will have 2 layers surrounding it. The very first layer will be because of the adsorption of the molecules inside. Now this adsorption is a chemical process. And the second layer which comes near this electrode is the Coulombic layer, is because of the Coulombic attraction, because of the charge which is there on that electrode. And this double layer which is formed there is actually leading to some kind of super capacitance or some kind of capacitance in a very, very small geometry in this small layer which is called the Helmholtz layer. And if you have such two such electrodes and connect them, then you are getting a very interesting phenomena which is called the super capacitance. That is different from the ordinary capacitor where you use a electrolyte which is a insulating material. It's a dielectric material there, but here the electrolyte inside it's something which is there in between is a ion conducting solution normally, or a solid electrolyte, ion conducting solid electrolyte also in our case now. So everything which is happening is because of the potential gradient at the Helmholtz layer, for example here or here, and then in between there is nothing, no electric field which is existing in between the electrolyte in the middle portion of the electrolyte. So if you have a huge surface area, then you can achieve huge charge storage at the interface. This is the electrostatically attracted charges. There is no Coulombic, there is no Faradic processes which are happening here, and therefore we get a huge capacitance provided you have a huge surface area at the interface. Now this is something which is a basic principle. But now we have a solid electrolyte, and how to make a supercapacitor also out of it. So one process which today I'm just discussing is the polymer conducting ceramic composites, which are used as electrolyte. Now these electrolytes have to be pressed now because the interface has to be smooth also. The type of Helmholtz layer expected, whatever we are forming, is required, and for this a good heavily highly activated carbon of about 800 to 1000 meters square per gram surface area is required. Now this we can prepare also, we can get it from somewhere also, and then the electrodes are ready for the work. Now the next job is to talk about the fabrication of these supercapacitors. So here we have to ensure that the electrolyte is very, very uniform. That means the solid electrolyte or the membrane which we are preparing has to be a uniform membrane, so that everywhere the thickness remains the same and the interfacial contacts will be possible. So here the ball mill assisted synthesis route was used by us in this process of preparation of this freestanding solid polymer electrolyte film, not the conventional route. And then we have used a simple lamination, hot roll lamination process by which sandwiching the electrolyte membrane between the electrodes, between the high surface area carbon electrodes. We have just let it go through the lamination machine, and then it gets laminated. So about 70 degrees of temperature, which is little higher than the melting of the polymer, is achieved, and this is able to establish good contact at the interface. So these steps are simple, and one can prepare these supercapacitors. These are now all solid contacts at the interface, and these supercapacitors are there. Now the electrical transport, as you can say, initially the films which were used for the fabrication of supercapacitors were not having very high ionic conductivity. This moderate conductivity of between 10 to the power -4 and -5 was used initially to initiate the work to see the effect, because initially we have to go with the lower things, and later on we can look for a better ionically conducting system and also optimize the things. So with smaller ionic conductivity, lesser ionic conductivity, we have initiated the work. And here this is the LiTFSI salt and polymer with little amount of PEG, and this LATP, which is the lithium nasicon structured lithium ion conductor, was used and dispersed inside with 30 to 40 nanometers of size. And this kind of slurry which is finally appearing was finally given a shape by hot polymer press machine, and with 200 micron film the supercapacitors were developed. Now some of the results quickly I will show you. The Nyquist plots here are purely showing the capacitive behavior of the supercapacitors. So here we can see when the salt is added more, then it is showing a more vertical straight line. So that means the role of salt is very much there. So salt plays an important role. The dissolved salt inside the polymer matrix plays an important role. Now there is no significant bulk impedance is seen here in this case, and that also signifies that indeed the double layer capacitor formation is there even in the case of solid interface. And then some kind of diffusive mechanism, Warburg nature, is also seen here. That also suggests a supercapacitor kind of behavior, which is normally shown by liquid and gel polymer based systems. So the nature of the Nyquist plots is similar to those of the other supercapacitors which are shown. The CV scans the hysteresis and the feature-less behavior of the CV up to a voltage of 2 volts we have taken, and we can see that when the salt is more, then also the box-like nature is visible, more apparent. When Nasicon content is more, then also box-like behavior is more apparent, and that means the electrical transport is more in the polymer matrix, then it leads to a better value of the supercapacitance. So that is what is also visible in the discharge curve when potential versus time is shown, and various supercapacitor films were used in various Nascon content polymer films were used as electrolyte. Then we could see that finally when the conductivity is high, then we are getting a better discharge, and the discharge is almost linear, though not completely, but it's linear like behavior, and it is expected that solid-solid interface will have certain amount of polarizations at local level, at various local levels. Therefore, it need not be a very smooth and straight line drop of the potential, but however, the nature of overall fall suggests that this is indeed a supercapacitor formation. Then these supercapacitors were also tested for a very long duration, about 16,000 cycles, and the capacity was studied, and other parameters were also studied as a function of time. And these are some simple relations which are normally used by everyone in case of standard relations used for the capacitance, specific capacitance, Coulombic efficiency, and energy and power, specific energy and power purposes. And what we find is that initially the capacity drops, and then finally at later times it stabilizes to a constant value. In solid state, I would say this is appreciable, particularly when the electrical conductivity of the electrolyte is not very high, and the efficiency is maintained above between 80 to 85% even after 16,000 cycles. And the interface, the solid-solid interface as shown here, is interestingly just a minute. Yeah, so is interestingly intact after the 16,000 cycles, and this is also very interesting. The overall parameters, if one see, is comparable to those of the gels. However, I have to admit that we have to work more on the energy density part, which is little less, but the power densities seem to be comparable here. Now, when the conductivity of polymer electrolyte is improved by adding more Nasicon to it, that means now it is polymer which is going into the Nasicon matrix and sitting in between the grains and somewhere between the grain boundaries, then the conductivity in certain cases is certainly higher than 10 to the power minus 4 at about between 30 and 40 degrees Celsius. And these are more useful systems for the fabrication purposes. So when one uses a high Nasicon content samples for the fabrication of EDLCs, then the impedance and impedance value is also quite low, and the overall discharge shows a higher capacity. And this higher capacity, is sometimes higher than, even also than some of the gel electrolytes which have been reported. So Nasicon content definitely plays a role here, and overall conductivity of the polymer electrolyte certainly matters, and that shows that it is not necessary to have a gel, but if the interface is made smooth, then one can get very good electrical transport, then one can get very good capacitance also. And this is indeed an interfacial phenomena which is happening also in the solid state. So more than 100 farads per gram capacity is seen, and the ESR value, whatever we have reported, obtained here is comparable to those of some of the gel electrolytes. Of course, it depends upon in the gel what is the content, what is the composition, but then if you see many of the gel electrolytes are showing comparable values to these ones. And this is appreciable also with respect to the fact that one can use it for glowing the LEDs. Say 2 watt LED with a all solid state supercapacitor, different LEDs could be grown, and up to 5 minutes of constant discharge we have seen for white, red and blue LED. And of course you have to make a combination so that the total voltage is more than 2 volts. So one of the cell can provide 2 volts of voltage here. So this is indeed a supercapacitor, and in the solid state it works quite well. So to conclude here, so first of all, the solid polymer electrolytes can also be used for EDLC applications, and for some compositions the performance is comparable to those of the gels, even with moderate ionic conductivity values. And when the ionic conductivity values of the solid electrolyte is higher, then in fact better results are obtained. Low power devices, certainly like the other solid state devices, these can also be used for the low power devices, and one has to look a lot of physics behind, one has to explore the physics behind the processes. That means what is the nature of the interface, what is the nature of the electric double layer which is forming at the interface, how the ions are able to diffuse in and out of those pores, that also has to be seen. And then finally, but still something is interesting and which is definitely happening here. And we are also working for the large surface area activated carbon. Right now this is a moderate value of somewhere between 800 to 1000, but I'm sure that when we use large surface area and when we improve the interfacial context, possibly this can be a very interesting new direction in which one can grow. Now this is my group, and these are some of the recent publications in which some of them are reported in one of the in this recent work, recent papers. And yes, so this is the work by my research group over here. So I'm done. So then I'm done.
All right. Thank you very much, Prof. Dalvi. Okay, I open for Q&A from the floor. Any questions? Prof. Dalvi, can I ask a question?
Sure, sure.
What is the range of the conductivity for Nasicon-based solid polymer electrolyte?
So when one looks for solid polymer electrolyte, then in-grain conductivity of Nasicons is reported somewhere between 10 to the power -4 to -5 ohm inverse centimeter inverse. Of course, there is it depends upon the way one prepares. So reproducibility is another issue in case of Nasicons. How much pressure one applies. But then in-grain conductivity is somewhere about 10 to the power -3. If someone uses LAGP, germanium oxide, then it is between 10 to the -3 and -4. But the germanium oxide is very costly, and therefore people avoid using it. When LATP normally is showing close to 10 to the power -3 in-grain conductivity. But in the polycrystalline form, it drops to 10 to the power -6 or -7 sometimes. Depends upon how we are preparing the systems. But in case of polymers, now it reaches to 10 to the -4 and even more than that in our case. When the Nasicon is dispersed in polymer or the polymer in Nasicon, we are getting a better conductivity. -4 to the -4.
Yeah. So Prof, so in your lab, so the conductivity highest achieved is about 10 power of -4.
-4.
Okay.
True.
So and you fabricate the EDLC. So what is the power density of the cell?
Power density I have reported in this one. It is somewhere, So if we see the highest one, it's about 530 watt per kilogram kind of power, which is of course the energy density is low, but this is the power density in solid state. This is for the poor systems, but the highly conducting systems, we are yet working on it. That I have not reported here. So this value is for the conductivity of -5, somewhere between -4 and -5.
Yes, this is all solid state EDLC. Yeah,
Yes.
all right. Okay, thank you from me, Prof. Dalvi. Any more questions from the floor?
Yeah, I have one small question.
Yeah,
Sure,
Prof. Bhattacharya.
Professor Dalvi, other ceramics like the heavy metal oxides and those things, can you comment that what will be their response?
Yes. So so far, whatever we have studied, we have seen that the conductivity of the dispersoid definitely affects the property of the cell. So if one goes for garnets, possibly one can obtain better, this hybrid composite, because garnets have very low grain boundary conductivity, grain boundary resistance. Therefore, garnets can be a proper choice, but the cubic garnets have to be prepared for it, and we are working on it. But then the idea of making nanoparticles of garnets and then dispersing them inside the polymer without hampering the structure of the garnets is another issue. Polymer, in my experience, is that these nasicons are little robust systems and easy to prepare also. But garnets means you need a lot of expertise in preparation. Lithium nitride can also be one of the substitute, and some of the perovskites can also be looked into for such applications.
Okay.
Yeah.
Thank you. Thank you.
May I ask one question?
Yeah, please.
Okay, so this is salt in polymer, right?
This is salt in polymer,
This
and
side means this is nasicon in polymer electrolyte. Composite electrolyte means.
Bilkul. But with active dispersoids. Normally, until last decade, people have been dispersing alumina, zirconia, yttria kind of insulating particles inside the polymer matrix. That used to lead to increase in the conductivity, but because of but there is a limitation. You cannot increase the amount more than 13-14 weight%, and you cannot make them of bigger size also. They themselves will act like obstacles to the ionic motion. Therefore,
so this is dispersed electrolyte.
These are dispersed electrolytes. Very correct.
Thank you.
Okay, thank you very much. So if you would like to, if you have any questions for Prof. Dalvi, I guess you can contact him via email. Yeah. Okay. Thank you very much, everyone, for joining me for session 6. So I will pass over the session to Professor Pramod. I pass over to you. Thank you very much.
Thank you, Neelamdi. I think my voice is clear. Any? Yeah. So thank you, Neelamdi, once again to giving me this chance to working as a session chair for. Actually, I am little bit up because most of person who is going to deliver to talk in my session, they are more experienced than me. But anyhow, I am thankful to provide me this chance, this opportunity to act as a session chair for, you can say, session 7. So in this session, I think there are 4 eminent speakers, and number 1, which I always like to be number 1, is none other than my best friend, you can say, Professor Tanwani. Now she is in front of me. So I think it is my privilege to welcome you here in the, you can say, in this conference, and without giving her permission to present her work, let me tell something about Professor Tanwini, because she is too much close to our, you can say, solid state ionic society. Her Professor Tanwini received her PhD degree in advanced material from Faculty of Science, University of Malaya, with Professor Arof group, and he is always, Professor Arof is always for us as a guru, and she is now a professor at the School of Physics and Material Science, University Technology Mara, Malaysia. Solid state ionics and energy devices are her main research area. She has published over 100 research papers in referred international journals, several books chapters, held several patents and copyrights. She has received several medals and awards in international and national events in her own repute. She is editor of book Polymer Electrolyte, which is very famous book, I think, for polymer electrolyte people, characterization technique and energy application. Guest editor for many special issues of Material Today Proceedings, Material Research Innovation, American Institute of Physics, editors in International Journal of Institute of Materials, Malaysia, IJIMM, and Science Letter. Apart from that, she has already used, or you can see, as expertise in working as a reviewer of, I think, many more international journals. Besides this, she is a very kind lady. I always close with her. She is an associate fellow of Malaysian Scientific Association, counseling member of Institute of Materials, Malaysian, you can say, 2014 to 2006, member of Malaysian Solid State Society and Technology Society from 2009 till present time. So with this brief biodata, now I request Professor Ta to deliver her lecture, and she is going to deliver her lecture on well-known topic. I think she might be clearly going to explain each and everything. So now I am requesting Professor Tan to start her deliver her lecture.
Thank you, Prof. Pramod, can you see my slide? Prof, can you see my slide, Prof. Pramod?
Yes, we can see.
All right. Okay. Thank you very much, Prof. Pramod, for the kind introduction. Nice meeting you today. Okay. Good afternoon from Malaysia. Okay. I'm Winnie from University Technology Mara, Malaysia. So
Your voice is breaking.
yes, there is some problem with the. Okay, okay, now the slide move. Okay, so for those who are not familiar with my university, so a quick introduction. So University Technology Mara, or known as the UITM, has campuses all over Malaysia. So we are the largest university in Malaysia. So I am from the UITM main campus, which is located in Shah Alam, about 28 kilometers from Kuala Lumpur, the capital of Malaysia. So this is the view of our Shah Alam main campus. Okay, so without further ado, this is the outline of my talk today. I will begin my talk with the differences between capacitor and battery. And previously, we have Prof. Delvi, which shared to us a very good analogy between the batteries and also the capacitor. He basically symbolized battery as a marathon runner, but supercapacitors as a 100-meter runner. A very good analogy. Okay, and I will share with you on the types of capacitor and a little bit of the sharing on the current commercialization of supercapacitor, then follow of some of my research work on single versus mixed transition metal oxide as electrode material in supercapacitor. Finally, on the performance of this iron cobalt type material in supercapacitor. So this is some comparison. So you see that capacitors and batteries. So capacitors, like batteries, they are also important energy storage device. So as compared to batteries, capacitors has high power density but lower energy density. So for a conventional capacitor that you can see shown in this figure, an insulating film is sandwiched between two metallic electrodes. So conventional capacitors store energy physically. It means that there is no major change in the structure of the materials between charge and discharge states. So on the other hand, batteries store energy chemically. So you can encounter physical change in the structure of the material between charge and discharge states. So capacitor can be generally categorized into conventional capacitors, electrolytic capacitor, and electrochemical capacitors. So electrochemical capacitors are also known as supercapacitor or ultra capacitors. So supercapacitors have the highest volumetric capacitance and the greatest charge density compared to other capacitors. So they basically bridge the gap between the conventional capacitors and batteries. So on the basis of charge storage mechanism and electrode materials employed, supercapacitors can be divided into two categories. So which are electrochemical double layer capacitor EDLC, which we have seen previously from Prof. Davi's presentation, and the other class will be the pseudo capacitor. So the charge storage mechanism in EDLC is non-Faraday, as shown just now. That means that there is no transfer of charge between electrode and electrolyte, but based on the accumulation of charges at the electrode and electrolyte interfaces under the application of an electric potential. And also carbon materials such as activated carbon, graphene, carbon nanotube are commonly used in EDLC. So basically, these three pictures show the charge storage mechanism of EDLC, where I will not go into details because this has been covered by Prof. Delvi just now. Thank you very much, Prof. Okay, so here are some of the performance of the EDLCs reported in the literature. So you can see that generally the power density and the energy density of EDLC are much lower as compared to pseudo capacitor. Yeah, okay. So the charge storage mechanism in pseudo capacitor is Faraday, means it involves the redox reactions and transfer of ions between electrode and electrolyte. So for pseudo capacitors, electrode materials are like transition metal oxides and sulfides, conducting polymers such as you can use polypyrrole or PANI. Okay, so pseudo capacitors employing transition metal oxide electrodes usually will show larger specific capacitance than EDLC. As I show here are some of the reported results for pseudo capacitors that I have compiled from the literatures. Okay, so here is a brief overview of the applications of supercapacitors in the current electronic and automotive industries. So for example, graphene supercapacitors have been used to power the Samsung Note 9 stylus. Now it's no longer Note 9, I guess Note 10 already, okay? In automotive industries, Supercapacitors can be used with batteries, okay, to smooth the power fluctuations, like stopping and starting at the traffic lights. So if a battery is paired with a supercapacitor, the supercapacitor could take over this during the starts and stops. So it could quickly deliver some energy, reducing battery wear and extending the battery's life. So already in Shanghai has a network of buses that run on supercapacitors. Okay, so as such, at each stop, the bus charges the supercapacitors and then it gives it enough energy to drive for 10 to 15 minutes to the next stop. So the supercapacitor market is projected to expand at an annual growth rate of 15% from 2018 to 2026 and is expected to reach USD 550 million by 2026. So you can see that super capacitor is a big market out. So like I aforementioned, I mentioned earlier, the major drawback of this carbon-based EDLC is the small specific capacitance, which then result in lower specific energy. Of course, there are different strategies to improve the energy density of supercapacitor, such as we can employ non-aqueous electrolytes or use asymmetric cell design, which benefit from wider electrochemical windows. However, one of the more efficient approaches to increase the specific capacitance is to take advantage of pseudo capacitance of fast and reversible Faraday pairs in the electrode materials. So bear in mind, 70% of the supercapacitor performance comes from their electrode materials. So among all available energy storage materials, transition metal families are amongst the most promising due to their large theoretical specific capacitance. So single oxide mixed transition metal oxides have been widely investigated for application in supercapacitors, so which has better electrochemical performance, the single metal oxides or the mixed transition metal oxides. So this is what I'm going to share with you, some results from our laboratories on the transition metal oxide based electrode materials. Okay, so we have the iron cobaltite and also a single metal oxide, which are the iron oxide and cobalt oxide. We synthesize using the hydrothermal process. Why we choose hydrothermal process? Because it has low synthesis parameters and it's cheap and good oxygen stoichiometry. So basically, these are the formation mechanism of, let's say, let me begin with iron oxide first. So during hydrothermal process, we have urea reacts with water and then decompose into ammonia and also carbon dioxide. Then the ammonia will react with water to form this NH3 H2O, which further ionize to ammonium and the hydroxide ions. So CO2, the carbon dioxide, dissolves in water to form carbonic acid. Then the carbonic acid ionizes into the hydrogen and also the carbonate ions. So the dissolution of the iron chloride tetrahydride, which is our precursor, will release the ferrous ions. Then the ferrous ions react with the carbonate, okay, and also the hydroxyl to form iron carbonate and iron hydroxide respectively. Okay, the formed iron hydroxide, okay, will eventually transform to iron carbonate as shown in this figure 6. So iron oxide can then be obtained upon calcination treatment of this iron carbonate at 400 degrees Celsius for 2 hours in air. Okay, so for cobalt oxide and also iron carbonate, both also synthesized using the same procedure, except for cobalt oxide, we substitute the iron chloride tetrahydride by cobalt chloride hexahydride. So during the hydrothermal process, the cobalt will react with the carbonate and hydroxide from the decomposition of urea, so to form the cobalt hydroxyl carbonate. This is the precursor for cobalt oxide. Then the cobalt oxide is obtained after calcination treatment of cobalt hydroxyl carbonate at 400 degrees Celsius in air. So this first equation represents the formation of the cobalt oxide. So for the synthesis of iron cobaltate, the same procedure was employed, but now is in the presence of iron chloride tetrahydride and also cobalt chloride hexahydride. Okay, different starting materials is used. So this second equation represents the formation of the iron cobaltite. So we synthesize 2 single oxides and also 1 iron cobaltite, and we also investigate their structural properties. So the structural properties of the as-prepared samples were characterized by XRD. So you can see that the diffraction peaks of the iron carbonate, which is the precursor, okay, to the iron oxide, they can be indexed to the rhombohedra of this to rhombohedra according to the library. So upon calcination, so we have the precursor converts to the iron oxide. So we match the diffraction peaks of the iron oxide with the library, and these peaks can be indexed to the rhombohedral hematite, okay, iron oxide. Okay, so we also do the same to check of the structural properties of the cobalt oxide. So these are the diffraction peaks of the precursor, cobalt hydroxyl carbonate, which the diffraction peaks after matching with the library, they are all indexed to the orthorhombic structure. Okay, then the precursor converts to the spinel cobalt oxide after calcination treatment, and the diffraction peaks are then identified using the library. Okay, so these are the diffraction peaks of the precursor materials for the iron cobaltite, which are similar to the standard pattern of the monoclinic of the cobalt hydroxide carbonate. Excuse me. And the peaks of the iron cobaltite can be indexed to the cubic spinel phase with space group of FD3M and lattice parameters of A equals to B equals to C equals to 0.824 nanometer. So this is what I would like to share on the overlay. This is the overlay SRD pattern of cobalt oxide and iron cobaltite. This overlay SRD pattern gives us 2 very important information. First, okay, oh, sorry. Okay, so you can see that there is a tiny peak shifting to the left, okay? And also white and weak diffraction peaks for the iron cobaltite. So shift of peak to the left suggests the expansion of the cobalt oxide crystal structure upon incorporation of the ferrous ions. Okay, the expansion of this crystal structure is important because it leads to the expansion of channels, which will be beneficial for the transport of ions and also electrons. So on the other hand, we can see that, you know, the weak and white diffraction peaks for the iron cobaltite suggest a weak crystallized structure of this iron cobaltite. So this weak crystallized structure can help in expanding or contracting, which can then facilitate the intercalations of charges during the electrochemical reactions. Okay, and we also counter check the structural properties using the FTIR. Okay, so these are some of the characteristic peaks shown by the precursor iron carbonate. So then the characteristic peaks disappear, okay, when the iron carbonate transform into the hematite. So the hematite can be indicated, yeah, by the presence of the peaks at 551 and also 587, which corresponding to the stretching vibrations of the iron and oxygen bond. Okay, same thing, we do the same, okay, for the structural properties using study using the FTIR for both the precursor of the cobalt hydroxide carbonate and also the cobalt oxide. So the presence of these are the characteristics for the precursor, and the composition of the cobalt oxide is indicated by the presence of peaks of at 553 and also 656. So these two peaks correspond to the stretching vibration of the cobalt oxygen bond. So we do the same thing. So these are the characteristic peaks as shown by the precursor. Okay, and again, deformation of the iron cobaltite is also manifested in FTIR study with two distinct peaks at 545 and also the 643. Okay, so we do an electrochemical property studies for these three materials, the single oxide and also the mixed transition oxide. So here is the CV curves. Okay, you can see here the red and also the black one. Okay, the CV curves for both cobalt oxide and iron cobaltite show a pair of redox peaks. Yeah. Okay. However, in contrast, the well-defined redox peaks are absent for the hematite. So the occurrence of the oxidation and the reduction peaks is due to the Faraday reactions. So this suggests that the pseudo-capacitive behavior of cobalt oxide and also the iron cobaltite. This hematite do not show any pseudo-capacitive behavior. So we done the GCD charge discharge curve. Okay, so these figures demonstrates the GCD curves of these three materials. The A is the hematite, B is the cobalt oxide, and C is for the iron cobalt oxide at various current densities. So we calculated the specific capacitance from the discharge curve of the GCD using these equations. Okay, where I here is the discharge current, M is the mass of the active material, VF, VI is the initial and final voltage of the discharge potential window. So the most important thing here is we calculate the specific capacitance. So here we can see the variation of the specific capacitance with respect to current density for these three materials. So you see, for all the current densities, the iron cobaltite electrode has the highest specific capacitance, followed by the cobalt oxide and also the hematite. So the higher specific capacitance of the iron cobalt oxide might also be due to its nanosheet morphology that I capture using the FISM images. Okay, I will talk on this in more detail in my following presentation. Okay, so we done an impedance, okay, EIS. So these are the impedance plots for these three materials. You can see the occurrence of the semicircle, okay, at the high frequency region by magnifying these figures, okay, in the right figure. So this is the magnifying figures of figures A. So here is their equivalent circuit representation. So RS is the internal resistance, RCT is the charge transfer resistance, CPE is the constant phase element, and W is the wobble impedance. So how do we get the RS, the internal resistance? Okay, the intersection of the high frequency on the Z prime axis will give the value of RS. So, and then the charge transfer resistance RCT is obtained from the intersection of the semicircle and the spike. Okay, this spike represents the wobble impedance, which describes the ionic diffusion at the interfaces, electrolyte and electrode. So we obtained the RS value. So for hematite, we have 1.75, and then cobalt oxide 0.61, iron cobaltite the lowest 0.44 ohm. So the same thing for the charge transfer resistance, where the iron cobaltite shows the lowest charge transfer resistance. So you see for both RS and RCT, the low resistance of iron cobaltite electrode can then be attributed to the efficient transport of ions and electrons as a result of the expanded crystal structure and the nanosheet morphology of iron cobaltite. Okay, and also
Yeah,
the weak
Professor Tan.
Yes.
You have 5 more minutes, please.
Pardon?
You have 5 more minutes.
Oh, 5 more minutes. Okay. Okay, can I just skip here, yeah? Okay,
Yeah.
then this figure shows the GCD curves of the iron cobaltite electrode as various current density. So you can see that the specific capacitance actually decrease with increasing current density, and at 3 ampere per gram, the highest achieved is about 2,800, okay, farad ampere per gram. Okay, however, you know, when we increase the current density from 5 to 25, only about 44% of the CSP is retained. So we will do something about it, and I will show you later on. Yeah. So this decrease in the specific capacitance with the discharge current density is actually common, because this is due to the difficulty in the penetration and the diffusion of the electrolyte into the electrode. So this is what I want to show to you on the synthesis of transition method. You can use various methods as listed here, but we choose to use hydrothermal. So this hydrothermal process, the size and morphology can be influenced by the synthesis condition, okay, type and concentration of reactant, reaction medium, and so on. So here I would like to share with you on how we vary the duration of hydrothermal reaction, and then we can get a series of the morphology of the iron cobaltite. Okay, so this is the morphology evolution of the iron cobaltite by varying the hydrothermal duration. So you can see that at 2 hours, we have agglomeration of nanoparticles. At 4 hours, we have the urchin-like structure, which looks like a nano needles. So when we increase the hydrothermal duration from 4 to 8, we have nano needles develop into nanorods. Okay, but the nanorods are still maintaining the urchin-like structure. So we increase the duration to 12 hours. Now the iron cobaltite evolves from urchin-like nanorods into the flower-like nanosheet structure. Okay, so you see that all these nanosheets are closely packed and interconnected, and you can see voids are actually formed between them. However, at 16-hour time duration, the nanosheets starting to diverge. Okay, so this is the 20-hour duration. So at 24-hour hydrothermal duration, you can see microcubes start to form. Okay, so this is the morphology of iron cobalt oxide can be effectively controlled by just varying the hydrothermal duration. So we do some nitrogen adsorption, desorption isotherms, and also on the BET to evaluate on their particle size and also on their pore volume. Okay, so we can see from this table that the iron cobaltite nanosheets, okay, as compared to nanoneedles, nanorods, and also microcubes, it has the highest specific surface area, highest pore volume, and the total area of pores. Okay, and we do the we done the GCD and also the CV in 6 mKOH electrolyte solution. So this is the CV curves, okay, and they have the redox peaks, and this is the GCD curves, okay, and we calculated the specific capacitance from for these 4 materials. So we can still see the nanosheets will show the highest GCD, which is now 3000, I cannot see clearly, 3000 plus, okay, farad per gram. So among all this morphology, the nanosheets shows the highest CSV at all the current density. So maybe this is due to the highest specific surface area and the pore volume for the nanosheet structure. So it means that they have more active electrochemical reaction sites and greater diffusion kinetics within the electrodes for this iron cobalt type. Okay, so this table shows the specific capacitance obtained by us as compared to other reported literature. So as currently, we shows a more superior performance than those reported in the literature. Okay, and this is the performance of the iron cobalt type in super capacitor. We do an asymmetric design, okay, with the cathode iron cobalt type nanosheet, negative electrode as the graphene oxide, 6M KOH electrolyte. So again, this is the CV curves of the super capacitors. So we have oxygen evolution reaction, OER, starts at about 1.7. So the fabricated asymmetric supercapacitor is then stable up to 1.6 volt. So we also do the CV curves at various scan rate, okay? So you see this is the very beautiful combination of the pseudo capacity and EDLC behavior because asymmetry. One end is the graphene oxide, the other end is the iron cobalt type. So it's a combination. Okay, so this is the GCD curves of the super capacitor. So the most important thing is after 1000 GCD cycles, our supercapacitor only retains 60% of its initial capacitance value, where we are in the lab working hard to increase, the cyclability of these materials. So we also calculate the energy and the power density of the supercapacitor. So the maximum energy density is about 14.5 watt-hour per kg, and the maximum power density is about 2,100 watt per kg. So this is the conclusion that I'm not going to read. And with that, I thank you.
So I think I must thanks Tan for finishing at least on time. And we have already running late. I think half an hour, just you can say delayed. And it is normally okay in this COVID pandemic situation, I think. But if anyone had question, means we have already send and each thing related to her email ID are available on conference website. So those who have any questions, please directly contact to Dr. Tanvini. So
yes, thank you very much.
Once again, we are thankful for joining us.
Yes, thank you, Prof. Pramod. Thank you, Prof.
And now I think I am requesting second one speaker. Maybe is none other than Dr. Deepak Kumar to give his presentation. Before giving him presentation, let me tell something about Dr. Deepak Kumar. So Dr. Deepak Kumar obtained his PhD degree in 2011 from the Department of Physics, University of Delhi, and he is assistant professor at Electronics and Mechanical Engineering School affiliated to Gujarat Technical University, India. Dr. Deepak Kumar has a rich experience of teaching undergraduate and graduate students for more than 10 years. So he has already guided over 25 students for their master thesis, along with his guiding 4 PhD students in his area of expertise, condensed matter physics. Dr. Deepak Kumar has the honor of being a member of several professional bodies, like he is a life member of Materials Research Society of India, MRSI, and of Indian Science Congress, ISC, to name a few. He has published more than 30 international papers on his own repute, and I know personally Dr. Deepak Kumar have already well-known, renowned reviewer in too many international journals. So with this brief introduction, now I am going to invite Dr. Deepak Kumar to give his talk on topic investigation on lime-based sodium and conducting polymer gel electrolyte for electrochemical application. So Dr. Deepak Kumar, now floor is yours. Please.
Thank you so much, sir, for introducing me. I hope I am audible.
Yeah, everything is okay. Carry on.
Thank you, sir. Thank you so much, sir. I thank you. I thank Professor P.K. Singh for the introduction. Ma'am, that is not possible. I'm very sorry for that. Yeah, yeah. And I thank Professor Neelam Srivastav for the invitation. And without wasting any further time, so I am proceeding with the title. I shall be presenting on studies on tetraglycine-based sodium-ion conducting polymer gel blend electrolyte for energy storage applications. This is how I have organized my presentation. I will be giving brief introduction of the field, some fundamentals of the polymer gel electrolytes, some investigations which we have performed on the blend-based gel polymer electrolytes, some studies on the TGDME-based polymer gel electrolytes, and some prospects and future challenges. We all know that India is largely dependent on the costly, pollution-causing, and exhaustible fossil fuels to meet our energy requirements. In view of this, secondary battery systems, which are having low cost, it is made up of from naturally abundant materials for electrochemical energy storage, is a need of present as well as of the coming time. For realizing any effective and efficient battery system, a continuous and dedicated R&D is required for designing better and better electrolytes, anodes, and cathodes. Let us have a look on the global lithium resources. We can see the Argentina is having almost 27% of the lithium resources. Bolivia is having 16%, Australia is having 11%, Chile is having 10%. And India as a country is not having even 1% of the lithium resources. Therefore, we must look for the alternate energy storage technologies. Apart from that, the lithium-ion batteries which are most successful as on today, they are having certain limitations. That includes the flammability, transportation issues, high cost, and low natural abundance. It is also having risk of rusting, therefore protection circuits are required. The shelf life is there, and it is sensitive to high temperature and also sensitive to the low temperature also. It is a developing technology, and whatever mobile phone or any gadget you are having, in the next 6 months or a year, the composition of the next market device will be having altogether different composition of the constituents. So considering this in mind, there are various alternate battery technologies such as the silicon-based batteries, room temperature sodium sulfur batteries, proton batteries, graphite dual ion batteries, aluminum ion batteries, zinc nickel batteries, potassium ion batteries. Our group is dedicatedly working on the development of sodium sulfur batteries and the magnesium batteries. Recently, we have started work on the potassium ion batteries also. If we have a look at the some advantages and limitations of the storage devices, then EDLC, if we think of the getting higher power density, they are the first choice. But the disadvantage that includes is they are having lesser specific energy. That's why people are developing the battery technology. The lithium-ion battery especially is having high energy density and low maintenance, but it is having a higher cost and suffer from various drawbacks as I mentioned previously. The sodium sulfur battery is a good aspect. It is having low cost, natural abundance is also very high, but it is suffering from shuttle mechanism and the capacity fading as mentioned yesterday by Professor Manthiram also. If we look at the other systems, so those systems are also in the developing phase, and each system is a package in itself. having some advantages and some disadvantages. So this we have published in Journal of Energy Storage few years back. Now, for designing all these electrolyte system which on the systems which we have discussed, there is a utility of electrolytes. The extremes are the solid electrolyte and other extreme is the liquid electrolyte. The liquid electrolytes are most preferred because of the high conductivity and better ion dynamics, but they suffer from leakage, transportation issue, flammability, corrosive nature, and many other issues. Therefore, people are working on the development of solid electrolytes. The solid electrolytes are having inferior ionic conductivity, transportation number is also low, the viscosity is also very high. So there are some drawbacks of these two extremes. So the compromise is the polymer based electrolytes. So polymer electrolytes are the ion conducting systems which are having the ion transport properties quite comparable with that of the liquid electrolytes. Such kind of polymer electrolytes can be prepared by having a polymer matrix which supports the mechanical stability and a salt solution which provides the free ions which moves in a system and provides sufficient conductivity to the device. If we have a look at the polymer electrolytes, a lot of variant of the polymer electrolytes are used. The solid polymer electrolytes are there in which only polymer and the salt is there. In the composites polymer electrolytes, the nanofiller or the macro size fillers are introduced. In the plasticized polymer electrolytes, some plasticizers are introduced. In the gel polymer electrolytes, they constitutes basically three constituents: polymer, salt, and a definite quantity of the solvent which is able to provide a gelification. If we have a look at the modifications of the polymer gel electrolytes, then you can tailor with the solvents. So glimes are used, carbonates are used, phosphates are used, ionic liquids are used, and you can also use a cocktail. Recently, we published a paper on the cocktail electrolyte in the Journal of Molecular Liquids. With the polymers, there are various choices available. You can use polyethylene oxide, PVDF, HFP, and PMMA. And salts can be lithium, sodium, and depending on the salt system we are utilizing, accordingly the system is named as the sodium ion conducting or the other systems. This is very important slide, and this has been published in the Journal of Energy Storage Material by us. This is having impact factor of 17. In this, we have mentioned the challenges which are faced by the most of the electrolyte system. This paper was focused on the sodium sulfur batteries. So the similar kind of challenges are associated with the lithium systems also and other systems also. Generally, the electrolyte systems are suffering from the low value of the ionic conductivity. The interfacial contacts are many a times not up to date, and they are not good, thereby resulting in a high impedance and lesser performance of the battery system. The capacity fading is another issue. Thermal stability is available for certain temperature, but at the extremes, that lower temperature or higher temperature, the stability is not as required for the application. Apart from that, the whatever electrolyte we are choosing, it should be low cost and environment friendly. The shuttle phenomena is linked with the sodium sulfur batteries and some other battery systems also. Dendritic formation, as such formation is seen in the lithium battery system, the similar kind of formation has been observed by many researchers in the sodium counterparts also. Leakage, short circuiting, flammability, there are also issues. So these are the major challenges which we have to address, and if we are able to address these challenges, then we can have a good polymer gel electric system. So here I am highlighting some important properties which our ideal polymer electrolyte system should possess. So it should be thermally stable in wide temperature range, including the extremes. It should possess high ionic conductivity, not the electronic conductivity, for the device application. It should be non-flammable, and electrochemical stability window, that is the potential window in which electrolyte is working without dissociation of the ion, that should be as high as possible. So these electrolyte system can be used in the rechargeable batteries, super capacitor, fuel cells, electrochemical sensors, electrochromic display devices, and the solar cells. Here I am presenting one research work in which I have tried to fabricate an electrolyte system with a polymer blend-based system utilizing TGDME as a solvent. And here I have utilized different kind of sodium salts. And some studies we have performed that I will cover subsequently. So in the XRD studies, what we observing is for the pure PVDF HFP, the peaks, the semi-crystalline peaks are observed at the 14 degrees, 17, 20, and 38. And these peaks are basically overlapped on a hollow amorphous region, which is observed from 10 to 25 degrees. Once we incorporate the salt solution we mean the sodium salt immobilized in the TGDME. So then we observe the peaks are reduced, but there is some indication of the salt which is there. Smaller peaks are observable. So to further analyze, the complementary studies are required to understand the big picture of the ion transport which is happening. So before we proceed with the detailed ion transport, firstly we have determined the ionic conductivity. The ionic conductivity has been measured for all the electrolyte samples, and for the electrolyte material in which NaBF4 was used, we observed the highest value of the ionic conductivity and lowest the bulk resistance value. The ionic conductivity of order of 10⁻³ Simon centimeter inverse at 20 degrees Celsius has been observed. Further, this ionic conductivity has been measured as a function of temperature also. And what we observe is the straight line feature has been observed. This basically indicates that the hopping behavior is there, and the film is maintaining this ionic conductivity of 10⁻³ in temperature range of operation from 303 kelvins to 343 kelvins. For further investigating the thermal behavior of the material, we have also performed the differential scanning calorimetry. We observe for the pure PVDF HFP film endothermic peak, which is a melting peak basically, which is observed at the 140 degrees Celsius. Once we incorporate the salt solution containing TGDME and the sodium salts, what we observe is almost all the electrolytes are having a melting temperature which is close to 90 degrees Celsius. So we observe that the electrolyte films are able to maintain gel phase in a quite satisfactory temperature range of operation. And further studies we were also planning to do, and we are not able to do because of the lockdown in our faculty. So in the meantime, we have I'm presenting you another research plan in which we have fabricated three kind of things we have chosen. We have basically varied the concentration of the TGDME, and we want to observe what is happening inside the about the ion dynamics behavior. So salt, if we talk about, then the NaTF is used. The solvent is the TGDME. So TGDME is used because of the excellent electrochemical behavior. It is able to support high ionic conductivity. It is less flammable, or you can say non-flammable. That depends on the choice of the salt and the choice of the polymer also. And it is very stable. However, because everything is not having all the properties, there are always some drawbacks. So drawbacks includes the low capacity, the discharge capacity if we are utilizing this system in a battery system, and polysulfide issue is also there. To address this, either blends are formed, or some people add some other additive as a stabilizing agents, and many a times fillers are introduced to alleviate these issues. We have for this electrolyte system also we have performed the conductivity studies, and for the electrolyte composition which is having highest TGDME content is able to provide the ionic conductivity at room temperature to be 3.6 10⁻³ Simon centimeter inverse, and a straight line feature which is governing the hopping behavior of ions and also indicating no phase transition because no such abrupt peaks are there. So this is also a good feature of the electrolyte system. To further understand the ion dynamics, we have performed the dielectric studies also, and such kind of formulation helps in understanding the ion dynamics and change in the dielectric behavior within the polymer cell electrolytes. So what we observe is the real part of dielectric and the imaginary part of dielectrics both have been plotted, and as a function of the frequency for different electrolyte compositions. And what we observe is at the low frequency side, polarizing effects are observable, and because of it the value of the dielectric constant is high. For the dielectric loss also the such behavior is observable. It is very important to notice that at the higher frequency sides the contribution is very negligible. This is basically indicating that at such high frequency dipoles are not able to orient themselves in the direction of the applied field, and that's why the contribution is almost negligible. Now, for further investigate the ion dynamics, we have performed the modulus investigation also. And for this, what we have observed is the modulus is represented by the M prime and N double prime. See, what happens is in the case of the dielectric behavior, we are able to observe the features at the low frequency side. However, at the higher frequency side, we are not able to observe the features. So that's why the modulus formulation, this which act as a complementary kind of study, is utilized, and we can see at the high frequency side we can see some feature. So here what we observe is for the highest dilution of the electrolyte material, we observe onset of the peaks, and such onset of the peaks are indicating relaxing behavior which is happening inside the electrolyte system. And apart from that, as the concentration of the TGDME is changing, accordingly there is inconsistency in the peak height as well as the shift in the peak position. This is indicating that significant change in the ion dynamics and the dielectric constant and associated conductivity behavior is seen. And as a function of temperature also, we have investigated this electrolyte system, the optimized one, and we see that there is a small change, a small shift is there, which is again indicating that the electrolytes are very good, and in a wide temperature range the feature of the electrolyte, the overall feature does not change. However, a small change is there in the relaxation peak, which is indicating the change in the relaxation time and further change in the various parameters like mobility and charge carrier concentration and so on. For investigating the electrochemical stability window of the electrolyte, we have performed the cyclic voltammetry, and for the chosen electrolyte system we are able to get working voltage range of almost 4.4 volt, which is good enough for electrolyte system. For this voltage region, we have also observed that no unwanted redox reactions are seen, and which is also a good part of the electrolyte system. If we have a look at the cyclic voltammetry with the reversible electrodes, with the reversible electrodes, anodic and cathodic peaks are seen, which is indicating the plating and the stripping of the sodium ions at the respective electrodes. The total ion transport number has been also been measured, and it is found to be 99%, and this is indicating that the materials are purely ionic conductors and having good ionic conductivity, will have good ionic conductivity. The cation transport number is also measured using the Vincent method, which is a combined AC and DC technique. For such technique, impedance has been taken before the polarization. That impedance is recorded. The impedance is recorded to be almost 1439 ohms. After this, the electrolyte is polarized and current is monitored as a function of time, and the saturation current and the initial current is utilized in the Vincent formula. And what we observe is we have determined the total ion transport number, the sodium ion transport number to be 0.37, which is quite good enough for realizing electrochemical systems also. We also performed some morphological measurements, and what we have seen for the optimized electrolytes, the porous kind of structure is seen, and which is expected to support the ion conduction within the polymer gel matrix. In the case of AFM studies also, what we observe is the maximum roughness height is observed to be sorry, 23.2 nanometers, with average thickness height is also quite low. Such heights are lower as compared to the other reports which we have seen in the literature. This indicates that the surface morphology is quite smooth sorry, and it may be able to sustain and retain more liquid component and give better ion transport properties. For this electrolyte system, the XRD investigations are also performed. For this, PMMA based electrolyte system can be seen to have the peaks at 14 degree, and in addition some humps are also there at 30 and 43 degrees. And once we incorporate the TGDME solvent having different concentration of the salts, sodium salts, then the peaks are reduced, and which is indicating the amorphous content is increasing. However, the feature of the NATF as a salt content is not gone, that is visible and can be seen around 43 degrees. So thermal investigations are also performed, and we have seen that electrolytes are able to perform well, and they are thermally stable up to 170 degrees Celsius. So the films, if sir,
now you have 5 more minutes.
Right, sir. Right, sir. I will finish in 5 minutes. Thank you, sir. So this thermal investigation indicates that such electrolytes can be utilized in rechargeable sodium-based batteries. The fabrication of prototype sodium-sulfur batteries. So the prototype sodium-sulfur batteries has been made using PVDF-HFP as a binder element, the sulfur as a main component, and activated carbon is also utilized. The prototype is made by sandwiching the optimized electrolyte between anode and cathode. And for anode, NaHg was utilized. We have performed the battery characteristics by measuring the open circuit voltage, the galvanostatic cycling testing, and impedance measurements using electrochemical analyzer drive SP1. Further, what we have done is the prototype studies has been performed, and this is the profile which we have observed for the OCV. You can see the OCV of almost 2.2 volts is observed, and that remains almost constant. If we see at the discharge capacity, the discharge capacity is good, around 670, more than 670 milliampere hour per gram of the active material. Further, we have seen the discharge capacity as a function of cycles also. So what we observe is the cell loses almost 43% of the capacity in the second discharge, and subsequently it is around 383 milliampere hour per gram. However, after the first discharge, the capacity reduction is negligible. So at the 10th cycle, we observed the capacity to be 302 milliampere hour per gram of the active material, which is again this 300 milliampere hour per gram of the capacity is also good enough for a electrolyte system. I would also like to mention that I have investigated that why this is happening, and so reasons of this capacity failure. So what we observed is as the repeated cycling is happening, the interfacial resistance is increasing, and that which is contributing to this capacity failure. The main reason of this capacity fading could be that we have performed these measurements in an ordinary glove box. If we are utilizing a sophisticated glove box of ppm order, then results could have been more better. So now I am concluding. So flexible polymer electrolytes are preferable due to high ionic conductivity, good transport number, ease of uses as electrolyte for device fabrication. the detailed dielectric modulus and other investigation on the sodium ion conducting polymer electrolyte have revealed these electrolytes and associated electrochemical devices can be commercialized after their optimization, encapsulation, lamination. We will also attempt to seek its commercialization as a viable technology. And some recent publication of this year, 2022. So one publication is in Journal of Energy Storage, and other in Journal of Electronic Material, and other in Material Today Proceeding. In 2021, these are the main papers of ours, which are in Journal of Chemical Papers, Journal of Molecular Liquids, Journal of Electronic Materials, Ionics, and this book or CRC Press, and Material Today Communication. Apart from these, there are some other publications also. The last, I would like to mention that on the occasion of Teachers' Day, I have been awarded with Vishwacharya Best Teacher Award by All India Council of Technical Education. The award was given by our Honorable Minister of Education, Sri Dharmendra Pradhan ji, in presence of AICT Chairman.
Great.
So thank you so much. I'm open to the questions.
Now I think I must thank Deepak for such a nice presentation. And
thank you, sir. Thank you so much, sir.
Yeah, those who doesn't know, I think I have a close collaboration with Dr. Deepak.
Yes, sir. Yes, sir. Yes, sir.
So I think now this session we can allow just one small question if anyone has.
Can I ask one question to Dr. Deepak?
Yeah, please.
Sure.
Please, this in sodium sulfur batteries, even people used in this, if you recall, in Ford
Yes,
cars
sir.
also in 70s they have used when they heated sodium and
Yes,
sulfur both as metals, and in between sodium beta alumina was used as a electrolyte.
Yes, sir.
Being a solid electrolyte,
Yes, sir.
that was the very first
Yes, sir.
application.
Yes, sir.
But now still we
Sir,
have
sir.
not understood the intercalation. I mean the new intercalation compounds which can be equivalent to or parallel with the lithium cobalt oxide kind of things, and we have to rely on sulfur, and that is very hazardous and dangerous material for future. So can you comment on what are the possible work going on for the sodium ion intercalation compounds, particularly as a cathode? I like your work. This is very interesting. But if you can just shed some light on
also,
the...
Sir.
Thank you.
I'm familiar with you very much, sir. And Professor D.K. Kanchan is like a very good friend. So,
very
yes,
true.
Sir. So coming to your question, so earlier at the Ford time, around 1970s, the system was based on the beta alumina. The ion dynamics for the beta alumina is entirely different. And for realizing such kind of systems for a sodium sulfur battery, the operating temperature was 300 degrees Celsius. And once you are operating sodium and sulfur at 350 degrees Celsius, what is happening is both sodium as well as sulfur, they are in the most reactive state and they are in corrosive form also. So that's why such kind of combination were not realized later, and ultimately research is almost stopped on the high temperature batteries. From the year 2006, the development of the room temperature sodium sulfur batteries has started, and this is altogether a different concept in which the beta alumina kind of solid electrolyte are not utilized. However, there is a lot of scope to utilize such kind of either the Nasicon type of structures and utilizing it for fabricating a electrolyte system. There is a huge scope, and if you could allow, then we can also think of doing some good work in a collaboration also.
Yeah, I think
I hope I have answered your question, sir.
I think Anshuman never satisfied with it. If you are not giving him answer, I think he's not in happy face. You can see it means you have completely satisfied Anshuman.
Sir, you can ask the specific thing which you have not in which you want more light to be put.
I think Deepak, may I intervene in this one? Because
yes,
since almost session is going late, please do not take it in another way. Now I am giving a chance to next one presenter. This is one my formality. Okay, thank you. Maybe
Let me jump in to just congratulate Dr. Deepak.
Thank you,
So
sir.
now I am
Let
coming
me
to
jump.
next presentation, and that one is by well-known, you can say, physicist Professor Amit K. Chakrabarti. Before going to start with his own presentation, I think let me tell something about Professor Chakrabarti. Dr. Amit K. Chakrabarti is currently a professor of the physics department and the founder, coordinator, and professor in charge of the Center of Excellence in Advanced Materials at NIT Durgapur, India. Dr. Chakrabarti received his bachelor and master degree in physics from North Bengal University and his PhD in such a huge topic, the synthesis and modification of carbon nanostructures. So he is going to tell many more things related to carbon nanostructure for electrochemical devices. Besides this, Dr. Chakrabarti recent research focus is on synthesis and application of nanomaterials for sustainable application. He has already published so many international reputed paper, and he has got very good, you can say, scientific project from Government of India, from not even Government of India, rupees 15 crore funded by various scientific bodies like from UK, Switzerland, and India. So he has already PhD scholarship from 2002 to 2005 of the Engineering and Physical Science Research Council UK, India Fellowship Award, and many more fellowship and award. So with brief bio data, I think Dr. Chakrabarti already published so many things, so many publications, so many, you can say, research innovation. Now I am not taking too much time. I am just inviting Professor Amit K. Chakrabarti for giving his presentation on carbon nanostructure for electrochemical supercapacitor. Professor Chakrabarti, please.
Good morning to everybody, and special good morning to Professor Pramod Singh, who has given such a nice introduction, talking too much, so many publications and all. Actually, he's a big appreciator, I must say. So I have not published so many papers as he has said. I feel I am still young, and I'm going to publish hopefully many more papers in the near future. So, well, actually, there are few people that must be thanked for that. So Professor Pramod is one for giving the introduction, and of course the organizers. I must thank the organizers for taking such an initiative to organize such a very focused conference at this pandemic time. And I did attend some of the topics in between from yesterday and also some lectures today. And what appears to me is that the organizers have done a very brave job and good job in finding the right speakers and organizing the different sessions and etc. So thank you, Professor Neelam Srivastav, for inviting me, for giving the chance to speak here, and all the organizers as well. And I have one special word for Pramod as well, because I think in Sharda University, ICEM, I was invited by you when you were the convener, you and Professor Bhaskar Bhattacharya. I see Bhaskar Bhattacharya is here also at Banaras University. So it's kind of a reunion for us. I don't know whether you recall that, but I did visit your university and I gave a lecture there as an invited speaker in 2014, ICSEM.
Yeah, you're most welcome anytime, sir.
Okay, so with this, I think time is short. We are running late, so I better start to the topic. So just for those who are not fully familiar about what is NIT Durgapur, I have a very quick slide here. This is the main building of NIT Durgapur, where we basically it was set up in 1960. In 2003, it was upgraded to National Institute of Technology, what we call today. 2007, Government of India announced it as a national center, as an institute of national importance. And right now we have several BTech departments, MTech and PhD, roughly about 600 PhD students, about 200 faculty members. And last year's ranking, we ranked 29 in India in engineering institutes, NIRF ranking. So with this, let me move on to the slide of the outline. So basically at the outline, I have the outline of my presentation is like this. So I briefly introduce supercapacitors, although I don't think I need to introduce a lot because the previous speakers have spent a good amount of time explaining those basics. Then I shall talk a little bit about the importance of hybrid materials as electrode for supercapacitors. Then basically I show 3 case studies of different kind of influences on electrochemical supercapacitors. One is influence of cation doping and carbon nanotubes on the electrode performance of some pseudo-capacitive material, which is basically in this case nickel hydroxide. The second case I shall discuss will be the case of, I can probably get a pen, highlight, maybe this one, yeah. So then I have this influence of different carbon nanostructures. So in another study, what we show is we compare 6 different types of carbon nanostructures on a given pseudo-capacitive material, that is nickel hydroxide. And then the last slide or last topic that I would like to share or discuss would be the influence of reduced graphene oxide on another system. So let us just move on one by one. So this is just one brief slide where I want to explain to you what is the concept of supercapacitors. But previous speakers like Dr. Salve, Dr. Tan, and also yesterday Professor Hasmi, they have already spent a good amount of time explaining the concept and the mechanisms of supercapacitors. So basically, see the top of the text, it says active material or electrode. So basically the electrode is the material that my research group has been working on. We have seen previous speakers, some speakers have spent time or doing research on electrolytes as well. There are groups who are also researching on finding out the right separators or developing new separator materials, but our focus has been mostly on developing electrode materials. So electrode is this. So basically electrode is the material which is directly taking part in the charge storage. So that is the reason why we focus on the electrodes. I think all well explained. So basically you have an electrolyte and you have 2 electrodes on the 2 sides. When you apply some bias, then what happens? The charges move from one side to the other. And depending on the material of electrode, you have different types of mechanism of charge storage. And that is also elaborated by several speakers. So I will also come to that in a moment. So what is a lot of time people ask me, those who are not from the field, they ask me, so what is the difference between capacitor and a supercapacitor? So that's the difference in the figure. You can see a capacitor normal or even steps use this kind of writings, 4700 microfarad, 16 volt, you can see, whereas the right hand side diagram shows 2.7 volt, but 3000 farad. So from micro, it is farad. So the supercapacitors, basically we expect that the capacitors should have very high degree of capacitance, right? The capacitance value is at 1 million times more than the normal capacitors. That is one very vague way of defining a supercapacitor. Of course, the reason is lying here because of the definition of capacitors. We have large surface area. By the porous electrode, we increase the large surface area, and also the distance is reduced very significantly. So these 2 factors contribute in getting a large enhancement in the property of the supercapacitor or the specific capacitance of the capacitor. So these are some applications. Again, some applications have already been explained. Professor Tan was mentioning that several buses are running in Shanghai using supercapacitors. So these are some applications, although so since this is not really my research topic at the moment or today's lecture, so I'll skip that part. So now my main focus is about the electrode materials. So for that, what are the choices before me? I have several windows which are disturbing me. I don't know how I can, because this is the first time I'm giving something on WebEx. How to get rid of the windows? Okay, I think I can't. Anyway, so here in the diagram, see at the top of my slide, I see a small window, a window of the same slide, miniature window of the slide. So that I'm unable to get rid of.
Yeah, Nilamji.
It is appearing as white box.
Disturbing.
It is due to network error.
Due to?
Maybe slow, yeah, slow.
Because we can see 3-4 white boxes only.
Yeah.
It is due to network error.
Oh, and you are not seeing the slide either. Are you seeing the full slide?
Full
Not
slide
the
we
full
can see.
slide.
Okay.
Network.
Okay, I'll try that. stop sharing.
You please go ahead. Please.
No better, right? No improvement.
It has changed, but not completely. Please go ahead.
Okay. So basically, the choice of materials for electrode can be classified two ways. So, in the previous, my previous speakers have shown there are two types of capacitors: EDLC, electrical double layer, and pseudo capacitors. So what I did is slightly differently. I am calling them double layer materials and pseudo capacitive materials. So for the electrode, so double layer materials behave like this, whereas the pseudo capacitive materials behave with through a redox active materials, which take part in some redox reaction with the electrolytes. That is what is shown on the right hand side diagram. And typical choice for double layer materials is carbon nanostructures, which have large surface area essentially. And but although even then they have some good properties, also some limitations. So for example, carbon materials have, despite being very fast and stable, often limited by their charge storage capacity, as the charge stored is purely by the electrostatic method. There is no redox mechanism taking place with carbon materials. Whereas pseudo-capacitive materials are usually transition metal compounds, sulfides, oxides, hydroxides, etc., which take part in redox reactions. So, so naturally, since redox reactions are sometimes, since they are ferritic, they can be little slow, and that is the reason why pseudo-capacitive materials are not, the power density may not be expected to be very high. So that is the reason. What if, and of course, this figure has been taken from a book that is coming up in this year, edited by me, co-edited by me. I would recommend, this is a kind of a publicity for me, so please excuse me for that. So this is a book that is upcoming, to be published by Elsevier, Sulfides and Selenides for Supercapacitor Electrode, in a book chapter in the book that is being coming up this year in June. So what about the hybrid materials combining both types? So the combining both types of materials is can this resolve the problem of, or not resolve the problem, rather, can this be beneficial for us? So that is so when you ask this question, let us first evaluate the goods and bads about the two types of materials. So the good properties of carbon nanostructures are that they are extremely thermally and chemically stable. They have high electrical conductivity, large surface area. Activated carbon especially has extremely large surface area, low specific mass. Their mass, because the density of carbon being a very light element, density is very low, so specific mass is very low. Whereas transition metal oxides, sulfides, hydroxides, etc., are very good in terms of catalytic activity because they take part in the redox reactions. They also have, most of them have good chemical stability and moderate surface area if you make them into nanostructures, depending on the structure that you make. Okay, so with this thought in mind, we design new materials for electrodes by combining these two types of materials, and which is basically hybrid composite materials for electrode of supercapacitors. So now, to begin with, before we move on to the carbon the influence of carbon structures, in this slide I am showing what are the possible carbon structures at nanoscale. So there are several carbon structures possible at nanoscale, and this slide is a very interesting slide. I like it very much. So this slide I have gathered. See, at the very top left corner, we have C60 fullerene, which is considered to be a zero-dimensional carbon because of its size of about 0.6 nanometers, which is made of 60 carbon atoms. Okay, so that's also, and this is a sp2 hybridized carbon. Carbon can also be found in nanoscale as carbon nanoanions, where basically the fullerene atom is coaxially encircled by a few more soccer balls. So one ball inside another ball like this. When that happens, then we can think of this structure as if it is a carbon nanoanions. On the right hand side, we have corner, you have nanodiamond, which is basically a diamond-like structure that is made of carbon. And then, of course, nanocarbon. Then, so this can be also thought of, this is a three-dimensional nanostructure of carbon. And then, is my slide moving or it is? stopped. The animation, I don't know. Okay, so then we have carbon nanotubes, and am I audible?
Yes, yes, you are audible.
Okay, because my slide seems to be frozen.
Yes,
okay.
It has frozen, but you are audible.
Okay, so let me try the next slide. So this slide basically shows all types of carbon nanotubes, and here at the center you see the rolling of a sheet, which is basically graphene, two-dimensional sheet, into a cylinder that gives us the structure of a carbon nanotube. And I am fortunate that I have, in my research of last 20 years, I have worked with all these types of carbon nanostructures, for something or the other. So my slide is not moving, which means I have to again restart.
You can do one thing, just stop the video.
Okay. Yeah, that certainly I can do. Yeah.
Okay. And try. Because you have network issue.
Yeah, it seems usually doesn't have other days. I don't know why I'm taking so many classes and lectures with this network. I'm not even able to escape. Okay, so I'm just pausing it. Stop sharing. These are the problems which is major concern for the organizers. Because you are running out of time and I am causing further delay to it.
This is the technical issue actually.
Professor
We can't
Chakrabarti.
handle.
Yes,
I
yes.
think it's okay. It is not due to Omicron. The society where I am sitting, it is in Omicron, Professor Bhattacharya. No. So carry on, it's okay.
Okay. Well, in my home also, my wife is currently infected, and I am safe so far. Yeah, it's everywhere. So let me start sharing again. Maybe I'll share again the slide first. That is helpful.
No, it is
Is it visible now?
Yeah, it's okay.
Yeah. Okay. So I begin my presentation with showing our own results. So in this slide, basically what I try to show is that we have conducted a study using carbon nanotubes on beta nickel hydroxide. And not only that, we have also combined this study with the influence of cation doping performed on nickel hydroxide. So this is a combined influence study of cation doping as well as carbon nanostructures on nickel hydroxide. Because nickel hydroxide we found is relatively less studied as pseudo-capacitive material compared to oxides. So we started with that. And then, of course, you can see it is published in 2019. So these are the high-resolution images where you can see nickel hydroxide, which is hexagonal. High-resolution image is shown here. These are like hexagonal structures, size about 35 to 40 nanometers, as you can see from the distribution. And then further SAED and EDAX confirms their identity. And the equation, the redox reaction that occurs in the electrolyte is also shown on the right-hand side, how the redox reaction, Faradaic reaction takes place. So this shows how we have developed a composite by attaching nickel hydroxide particles on the surface of the carbon nanotubes. You can see some carbon nanotubes here lying on the bed like this. Okay, so when we tested this, we got the different electrochemical properties, and the electrochemical properties are reported here. So on the first slide here on the top corner, slide A, is comparing the cyclic voltammetries recorded at different scan rates for the undoped sample. Okay, so just pure nickel hydroxide undoped sample. And then you can see the numbers, that is the specific capacitance calculated, they go down as you increase the scan rate, which is very straightforward, which is common. Everybody knows that. And then if we compare the undoped and doped as a function of doping concentration, then we see at 0.5% lanthanum doping, this value has increased from 390 to 462. At 1%, it has doubled to 911 farad per gram. At 2%, again, it goes down. 5%, it goes down further. 7%, it goes down further. So that means clearly we see a strong influence of the dopants, cation dopants, lanthanum cation dopants, but the influence can be positive or negative depending on the dopant level, how much doping we do, because basically at very high doping, it is not good anymore, because you create a lot of defects, and also the formation of, we have found out from the XRD and XPS that there is some lanthanum hydroxide formation, which is very poor conductor of electricity. So at high doping, this is what happens, and that causes the decrease in the property of the electrode. So simply these numbers are plotted here as a function of doping concentration, and you can see at 1% doping, we get the highest number. So that is basically kind of optimized doping concentration. And then we further show here current density versus voltage, that is against different scan rates. And as usual, like this curve here also, the scan rate increase of scan rate means decrease of the specific capacitance. So these are standard. So now, if we to investigate the charge discharge characteristics, it's also always important when you measure the specific capacitance from the CV. It is sometimes it is also important that these values actually are corresponding to the values measured by charge discharge, because ultimately you also have to check how stable your how many cycles of stability, cycles of testing you can do with this electrode. So for testing of cycle stability also, it is important to study the charge discharge characteristics, and here you have plotted the charge discharge characteristics as a function of different current densities, and of course, as shown by Professor Tan also, that as you increase the charge current density, the values significantly reduce, and that's a common phenomena, and there is a lot of research on how to improve these things. But so then at current, but however, despite the fact that at 4 ampere per gram current density for the undoped sample, this is so narrow. When we use the dopants at 1% lanthanum doping, we get the green curve, which is much larger than this curve here. So that means the dopant has made a significant contribution to the improvement of the property of the electrode. So if you plot this, and then again you get at 4%, 4 ampere current density. If you plot the specific capacitance, we see that the highest specific capacitance is obtained at 1% doping, which is consistent with the CV results. CV and GCD conform to each other, and we have shown here the further at 1% lanthanum doping, the influence of different current densities, as usual, the highest current density can be gives us the lowest value of the magnitude of the specific capacitance. So then what is next? The next is that we also thought that, okay, we have studied the influence of dopants. Can we study the influence of electrolyte? So electrolyte, we have tried 3 different electrolytes, sodium hydroxide, sodium sulfate, sulfuric acid. These are the most common electrolytes that are usually used by different researchers for supercapacitor development, especially for aqueous electrolyte. So because in my talk, I must mention that all our supercapacitors have been, electrodes have been tested with aqueous electrolyte, not ionic electrolyte. So our windows are limited to less than 1 electron volt, 1 volt. So here you can clearly see an influence that, okay, with sodium hydroxide, the values we have got 911 farad per gram, but when you change it to sodium sulfate or sulfuric acid, the numbers significantly get reduced. So of course, there is a strong influence of choice of the electrolyte. Similarly, now when you choose an electrolyte, is there any influence of their concentration? Okay, so this is the EIS curve. So this is the EIS curve also. So to understand this reason, we also did the EIS curve, and in the EIS we see that the charge transfer resistance is much smaller for the sodium hydroxide, which you can measure by the radius of the curve here, the small curve, the black line. Okay, so black line has the smallest radius, that is the 1 molar sodium hydroxide, whereas the other curves here have much larger radius of curvature of this circle, semicircle. So that is probably the reason. So basically the charge transfer is not as easy as it is in the case of sodium hydroxide. And that is the reason for such a low performance of the other electrolytes for our electrode system. Now, if we look at the influence of different molarity, then since we know that sodium hydroxide is the best one, so we have also studied whether it is 1 molar or 2 molar or 5 molar, what molar, because in the literature, many people test with 6 molar, some people report with 3 molar, right? So we thought, okay, we'll take a study how it is in fact influencing the parameters of specific capacitance. And we see that as we increase it up to 3 molars, the capacitance values are still increasing. But when you go further to 3.5 molar, it is 1153, it got reduced. 4 molar also it got reduced. So that means even though the electrolyte concentration has a positive influence, but that is not unlimited. After the concentration is significantly increased, then it is no more helpful. So that is why you have to come to an optimized concentration. And also at higher concentration, another factor that comes into mind that you have to one has to take care is that at higher concentration of electrolyte, especially alkaline electrolyte like sodium hydroxide, there is a factor of the corrosion of the electrode upon several cycles of cycling stability. So if you want to test the electrode after 5,000 cycles, what we observed is that at 3 molar concentration, the stability is not as good as it is with the 1 molar concentration. So we decided that, okay, we'll report everything at 1 molar concentration instead of 3 molar, despite the fact that 3 molar gives us, yes.
Sorry, register you. You have 5 more minutes left.
5 more minutes. Okay, no problem. No problem. I'll go slow. I'll not discuss all the topics that I have included, but I think I'll manage. Okay. Thank you. Thank you. Okay. So what happens is we thought of we compared here that different molarity versus specific capacitance measured by GCD. So here it is calculated from the specific cyclic voltammetry. Side by side, we have also calculated these values from the charge discharge measurement. And we see that the numbers are, although not exact, but they are not very far from each other. This is 911, this is 889. So the numbers are quite well and consistent. And the good thing is that at 3 molar in both CV and GCD shows the highest value of specific capacitance. And any higher concentration leads to further degradation of the specific capacitance. So next in line is to investigate the reason for it. So again, we do the EIS of different concentrations, and we find that at 3 molar concentration, the charge transfer resistance is least. This is about 0.58 ohm. The radius is almost invisible. The curvature of the semicircle is almost invisible. So it's very low resistance. And that is the reason why we get such high specific capacitance. And if you increase it further, then what happens? The value increases from 0.58 to 2.91 and from 2.91 to 8.95 just by increasing 1 extra molar of molarity of electrolyte from 3 molar to 4 molar. From 0.58 it goes to 8.95. So there is something serious happening. And when you compare the CV data with the CP data for specific capacitance, we see that 3 molar gives the best values, and 1 molar is also 1 molar is here, 2 molar is here. It increases, but after 3 molar it decreases. Then we also studied the influence of temperature, and the temperature influence, what we see here is that even temperature can increase the capacity up to 40 degree. It increases to 1900 from 900, so almost double from 25 degrees Celsius to 40 degrees Celsius. But above this temperature, if we heat further, then the effect disappears. So you don't get any improvement, and that is also confirmed, and the understanding has been made by comparing this with the EIS, and EIS also confirms that at 50 degrees Celsius, the resistance, charge transfer resistance increases, and 68 is in further. So this is how that study was over. So now we thought, okay, we have studied the influence of carbon nanotubes on nickel hydroxide and combined influence of dopant. So what about the studying the influence of different carbon nanostructures? So for that, we chose 6 different carbon nanostructures. So in the schematics, you can see that what I show here is 1-dimensional carbon nanostructures and 2-dimensional carbon nanostructures. In the 1-dimensional carbon nanostructures, we chose 3 different carbon structures like single-wall carbon nanotubes, multi-wall carbon nanotubes, and carboxylic acid modified carbon nanotubes. So 3 different carbon nanotube structures. And in the 2-dimensional carbon nanostructures, we chose graphene, that is graphene oxide, and then we also chose reduced graphene oxide, and we also chose commercially available GNP, that is graphene nanoparticles. Okay, so these 6 different carbon nanostructures we chose by taking same weight fraction, about roughly 7 weight percent, 6 to 7 weight % of carbon nanostructures, and rest we combined with nickel hydroxide, the same material that we have studied earlier. So nickel hydroxide was combined with 6 to 7% of carbon nanostructures, and then we tried to see their influence, which composite performs the best. Because in the literature, people have often claimed that somebody claims, okay, by putting carbon nanotubes we get this much of increase. By putting carbon nanospheres we get this kind of increase. So it was puzzling my student. It was actually the idea was purely my PhD student's idea. He was reading literature and he says, sir, we don't know whether graphene to choose, whether GO to choose, whether RGO to choose, which one is the best? We never know because literature is so diverse. So I said, okay, then we can try a comparison on a single system. So that's how in the slide you see 6 different carbon nanostructures. Here multi-wall carbon nanotube, single wall carbon nanotube, single wall nanotube combined with modified by COOH. Then this one is pure GO on nickel hydroxide. This is GNP, graphene nanoparticles, and this is RGO on nickel hydroxide. And then when you combine all these together, this was published, by the way, in Journal of Physical Chemistry C. And these are the different curves. All the curves look very similar because it's essentially carbon nanostructures with nickel hydroxide. So pseudo-capacitive influence is very strongly prominent here because we are using only 6 to 7% of carbon nanostructures. The behavior is still dominated by the pseudo-capacitive behavior. And I will not detail. So basically the summary of the previous slide is here. And when we see the GCD, charge discharge characteristics at 3 ampere per gram, then we see this comparison. And clearly the pink and the green ones are the highest, which are basically single wall carbon nanotube and RGO, pink, RGO. Okay. Here also on the right hand side, we compare influence of different current densities for RGO, because RGO gives the best result. So we compare the RGO with the different current densities, and the total specific capacitance compared for all these composites is compared here. And you can clearly see that RGO nickel hydroxide has the highest value, about more than 2000, whereas single wall carbon nanotube also gives pretty good value, close to 2000, 1800 or something. So when we compare the cyclic stability, we see that about at 5000, they are all pretty much stable. Even up to 5000 cycles of stability test, they show 80% charge retention. Okay. So when we compare the reason why RGO gives the best result, so for that we tested this with EIS, and from EIS also we see that the RGO has the lowest value of radius for the semicircle. So that is the reason the charge transfer resistance is small for RGO. But is this all? Is the charge transfer resistance the main reason for the difference? So to investigate that, we also compared the different specific surface areas of all the structures, and we found that the specific surface areas of RGO composite has the highest. It is 118, and next to it is 87, which is for single wall carbon nanotubes. So we find that the relationship of specific capacitance is not purely dominated by the charge transfer resistance. Rather, it is a compound function of charge transfer resistance as well as the specific surface area. And this is what the bottom two curves actually was suggested by the reviewers. When we presented this, the reviewer suggested that why don't you try to find a plot, because this is missing in the literature at the moment, that what is the relationship with surface area with the diffusion coefficient, because diffusion coefficient is a direct function of the EIS, the charge transfer resistance from the Randall circuit. So that we related, and we find yes, for RGO, since it has the highest surface area, it has the highest diffusion coefficient, so the charge transfer happens very fast. And when you combine this effect with the RCT, the charge transfer resistance, that is also we see the similar effect. Here, RGO has the lowest value of charge transfer resistance. Okay, so this is a major finding in our opinion. And from that onwards, we decided, since the RGO is the best material, so since then we decided, okay, most of the time we will prefer to combine our pseudo-capacitive materials with RGO. So next work that we did was combining RGO with CEO2, Syria, another metal oxide, transition metal oxide, which is recently published in Applied Surface Science. So here I am not going to show much details. So here we have from the, yes, time is up, right? Yeah.
Now you have to conclude.
Yes. I think it is the last slide. So what's key here, even with the RGO composite, the influence of RGO we studied, and we found that yes, at about 7% of concentration of RGO, 3 composites we prepared, that gives us the best value of specific capacitance. So RGO does have the strongest influence, and also you have to optimize the RGO concentration. So to take home the message, I would say that we have got certain conclusions from the research that controlled doping with cations can improve the surface area and conductivity of metal hydroxides, and thus it can improve the electrode performance for supercapacitor. Carbon nanostructures can also improve the specific capacitance of electrodes when combined with pseudo-capacitive materials. We have shown this. Of the 6 carbon nanostructures we tested, RGO has given the highest positive influence on the electrode performance, and there is a close correlation between charge transfer resistance and diffusion coefficient and surface area of the electrode material for its performance. So with this, I would like to thank my co-researchers, especially most of the work that I presented today is from my former PhD students, who is now a postdoctoral researcher with Sagar Mitra, professor of IIT Bombay, and my collaborators from Open University and Liverpool University in England. Funding has come from DST, MHRD, and NIT Kolkata. So thank you for your attention, and I am open to take some questions if there is any.
Thank you, Professor Chakrabarty, for such a nice, enthusiastic lecture. I think, of course, there are several questions, but time do not permit us. I think, yeah, of course, since my dean sir is in front of me and my senior, I had to, at least he had to ask one question.
Only one question. You have categorically, Dr. Chakrabarty, you have categorically used variety of carbon derivatives from RGO to the NPs. How about the quantum dots? Can you comment that if you use quantum dot, because the surface area will be too high, the conductivity will also, the charge transfer is expected to be pretty high?
I think quantum dots, yes, it's a very legitimate question. When we started the work, it was quantum dots we did not think of, because mainly because quantum dot is a relatively new concept, and I have been working on carbon nanostructures before. So I said, okay, these are the structures I know. So I suggested these 6 structures, which also are readily available at my lab. And quantum dot itself is not well established. You can't buy commercially, so you have to develop it first. And whether that is the best quantum dot, that remained a question. So that's why actually we did not study it. But I can probably comment that you are right that the surface area will be very much increased. But what about the conductivity? Because quantum dots probably does not help making a good network unless you are able to do that. So I am not pretty sure whether quantum dot is really going to give us benefit, because overall this will be a competitive process. Whether one side you get the benefit of surface area, the other side, unless you make a good network, since the pseudo-capacitive materials are themselves not good conductor, by having carbon nanostructures in a network fashion, you actually improve their conductivity. So having quantum dots which are not connected to each other, they may not be of help. That is my feeling.
Anyway, we can discuss this later, because Professor Pramod, he has already established the quantum dot nanoparticle network in polymer matrix, and he had used that. Probably we can discuss these things later. Thank you.
Sure, definitely. Yeah. So that problem has to be resolved. If its network is produced, then certainly that will be good. I'll be excited to see.
You can discuss this with Pramod. Sure. Pramod is the expert.
Sure. That's the reason why
we can prepare carbon quantum dots and share with you.
I think most of you have already seen it. I cannot deny it, but time do not permit us. This is our basic thing with solid state atomic society. So I think related to any query, we have already Professor Chakrabarty email ID. Anyone can reach directly and discuss so many things. So thank you, Professor Chakrabarty, once again for giving such a nice, wonderful talk. And now, without taking too much time, now I am coming to last speakers with this session, Dr. Pritam Singh. About Dr. Pritam Singh, I think Dr. Pritam Singh, I am a little bit have his CV in front of me. Let me discuss. Dr. Pritam Singh is an assistant professor in the Department of Ceramic Engineering, IIT BHU. His area of interest are energy materials, rechargeable batteries, fuel cells, hydrogen production, and renewable energy. He obtained his PhD from solid state and structural chemistry unit, IISc Bangalore. Dr. Pritam continued his research as an institute postdoctoral fellow at IISc Bangalore with Professor M.S. Hague. He has also had the opportunity to work with well-known Nobel laureate Professor J.V. Goodenough at the University of Texas, USA from 2011 to 2015. Dr. Pritam has 3 USA patents and 3 Indian patents to his own name. He has published over 50 research articles in peer-reviewed international and national journals. With these brief biodata, now floor is open for Dr. Pritam Singh. Please.
Thanks, Professor Pramod, for nice introduction, and I don't deserve that much. And see, we are the part of the ecosystem and trying to work here. So I thanks Neelam Madam also for giving me opportunity and for this wonderful the session he's organizing on energy materials, because these are the topics which are little less covered in India. Yeah, I'm audible?
Your slide is not means you have to full slide screen.
Yes, yes. I'm audible? Yeah, it's a full slide now?
Yeah, right now.
Yeah, yes, okay, thanks. So see, my topic is transition metal auxiliary supercapacitors and alternative routes to the lead acid batteries and inverters, what we are talking about. That how we can go ahead and develop the batteries come capacitors. So that's the topic of the talk is. And as we know that energy storage is one of the key challenge we are facing in this century. And why we are facing? Because of the fossil fuel to the renewable energy problem. See, we want to shift to the renewable, and we want to go away from the fossils. But when it comes to the renewable, most of the renewable energy is actually scattered and type dependable. So that's the way energy storage is very key challenge. Until unless we don't store that energy into the battery or the capacitors, we cannot use them. So energy storage is a compulsory requirement for the renewable energy sources, and we are trying to work on that and see that how we can couple it. And energy domain is already well established after the establishment of the lithium-ion batteries. So if you talk about the energy storage materials, the devices comes to our mind is either it's the capacitors, double layer capacitors, EDLCs, dielectric based capacitors, or the pseudo capacitors, or the lithium-ion batteries. The two we know very well known, the double layer capacitors or the lithium-ion batteries. If you think of the double layer capacitors, so they are the starting devices. So they cannot consider too much as a storage devices, but they are like a boosters who can provide the ignitions into the auto ignition devices, auto combustion engines, and all those places. And the battery, which is well known, has taken the portable electronic revolution. And in between, the new things coming into the picture is pseudo capacitors or the hybrid battery come super capacitors, what we are talking to develop. So as we know that this total energy, especially the renewable sector and all, is generalized through the lithium-ion batteries. And thanks to Professor Goodenough, who invented this lithium-ion batteries concept, especially of the lithium cobalt oxide as a cathode materials. And that has taken to the world into the next generation of the portable electronics. And whatever we are seeing currently is the phenomena of the lithium-ion batteries. And that's the way energy storage become very important. And that has provided a path for the energy storage from the renewable sources that can be utilized for the static usage or the control usage. Otherwise, you cannot use the solar, wind, or any kind of energy into the direct devices due to the unavailability of the fixed current. So batteries can act, and lithium-ion batteries especially comes as a storm. See, even though lead acid batteries were there before and other kind of batteries, but without lithium-ion batteries, means the high energy and high charge under the very small volume that comes through this has galvanized the electronics domain. And from the bulk telephone to we have shifted to the cell phones, and now from cell phones to the whole computer is inside our mobile phones. So that's what the changes the battery or energy domain can make. So, and that's why the world is now gripping for the new stages and what is beyond the lithium-ion batteries. So those are the things. Even Professor Goodenough contribution is not only lithium cobalt oxide, but he also made the LiFePO4, the safest batteries are LFP batteries currently coming. So the total energy domain, he has a huge contribution, and we just move that. So what lithium ion has done, that due to this ideal suitability in terms of weight and potential, it has made that much more compact device in the form of energy, and it has a very safe and relatively low corrosivity compared to the nickel cadmium and other things. So the lithium ion batteries came into the very long way in that one. However, the several problems are also associated with that, ranging from the lithium cost, its distribution, but more about the device itself. Because when we see, it's the greed what increase. If first we don't have the energy storage, then we want that, okay, lithium ion battery, at least we get up to electronics. Now we want for the EVs, now we want the storage for the bulk devices, now we want to regulate our grids so that we don't have a transmission line losses, we can minimize that one during the grid failure and all. So these kind of devices now needing that much different performance. And if you see the current batteries or the lithium ion batteries are specifically suffers when you expose them for the high current rates, charge and discharge. If the charge discharge rates are very high, their performance are very low. There will be sudden degradation into the batteries as well as the bursting of the batteries. So the Ragan plot already tells that the relation between the power versus battery energy is not very much favorable in the form of lithium ion batteries. And that's why once we are going for the much higher, at least the much power, superior power solution is having the same energy what the lithium ion batteries are having currently, we have to look beyond that one. And that's why people are looking at what can be done. So as we know that our first one, to get the solution, we have to ask the right questions. What are the right problems? So the current problem world is facing is the power capabilities, the energy storage capabilities. So see, because our now energy storage demand has increased enormous. Now we want to make the energy storage at the grid level. So we want a bulk storage devices so that we can store the energy from a solar power plant or the windmills are coming, and then we can deliver at the space that it can be required. So now we are looking for the grid scale energy storage, and then also the battery device should have that the low weight, low impedance, and the portability is another important phenomena which is still associated with the energy storage devices. So during means we have to trade off between the performance and the things, so that how we can do the bulk devising, how we can go for the energy storage. And now I see the energy demand has completely changed. Now we have a battery demand for the grid is around 29% and 38% about the transportation. So we have to work for that one, and how the solutions are going for those sectors, not for just the residential, commercial, portable electronics, even this one. So as our requirement is changing, now we have to change on our energy strategy and the working structure. And so that's why the personal electronics have less than 2% contribution. So that makes that we have to go beyond that one, and then we have to see that what the battery and super capacitors offers. So if you see the batteries, they are generally low power devices, have a good energy capability, and that can be utilized. But if you talk about the super capacitor or ultra high capacitors, the dielectric based capacitor, they have very high power, but they don't have a very relatively long cyclability, but their energy density is quite low, that cannot be utilized as a energy storage purpose. So we have to do something. What is the mixing of this? Can we get the hybrid, means instead of the very marathon racer which we can consider like a battery which have a high energy, or the sprinter of the 100-meter race like a capacitor? So can we get a mix? And that's the way. So how we can increase a specific energy and specific power into the single batteries. That is the fundamental questions world is asking if we are going for the grid storage or the bulk storage of the energy and the bulk delivery. So in that one, if you see the new things coming as a light is the lithium-ion capacitors or the metal-ion capacitors based on the pseudo capacitors in the term of energy and the power profile. So this power profile should go diagonally, and that's the way we can match it. So lithium-ion batteries, nickel MH and latest batteries are still at the good values, but we have to go something beyond, taking this into the forward mode. So that's the way what we are looking for. And then that's the energy and specific demand is there. So this diagonal cycle we want to increase. So we want essentially actually the either by increasing the power of the energy devices or the energy storage devices or battery, or if we consider in terms of capacitors, we want to get the increase the energy density of a capacitors. So that's why this is a momentum shift time into the battery research. See, the whole world is almost stabilized on the lithium-ion region. Lithium-ion battery is at the stabilized scale, and even if we do very much radical change research in India, then also we are not going to substitute anything substantial on lithium-ion batteries. And that's the well-established documentation for that even if you want to make the lithium-ion batteries for everything, we are not going to compete with the China, Japan, and Taiwan. But what the area coming new, if we do there something substantially better, we may able to take the lead position or the equivalent position to the world. And that's why even our country and everyone is looking for the new technologies. Can we do better at the grid scale? So electrochemical hybrid supercapacitor and the metal ion capacitors, especially for the EVs or the grid storage capacitors, are coming to the new light. And that's why we are looking for the similar chemistry, what is happening into the intercalative materials. Can we extend it into the high energy and high power performance, and can we get similar kind of materials which can enable it? So that's why surely the intercalative materials of the layered oxide is a base material, but taking that into and into the new limit or new height, that's our aim, and where not our aim but the whole world is coinciding. So the momentum shift is on the supercapacitors, and how people want to go for the supercapacitors are, see, from electric double layered and pseudo capacitors, can we go for the hybrid capacitor, where one electrode is acting like a battery and another electrode is acting like a capacitor. So in that you can get a reversible or the equivalent high energy, high power demanding situations. So, and that will give you the potential application for the EVs and grid storage, and that can even replace the lead acid batteries, because see, other than compared to the European or American world, the third world countries or South Asian countries are facing another problem, because we itself have a huge requirement of the inverters for our household energy challenges. And in that one, especially India, Pakistan, Sri Lanka, Bangladesh, this region has a huge usage of the lead acid batteries, the toxic lead, which is means a huge corrosivity and toxicity there, and that must be removed at earliest. So our major target is, can we replace this lead acid battery, and at least we can go for this level of the bulk energy and power storage what lead acid is delivering to us. Then only we can think of the new things, and that's why we envisaged to the new capacitors or the new type of metal which can do that one. As the hybrid supercapacitors are known, a lot of activity is going on the Faradayan mode of the energy storage, where you get the surface storage coupled with the bulk storage or the bulk reduction of the materials. And the choice of materials generally come with the, even our earlier speakers and all told about the spinel based materials and coupled with the carbon anode. So see, even though in the capacitor both plates are equally responsible and none of them is actually acting as a cathode or anode, but then also for the general understanding, we can tell them, even because this now we are looking for the capacitor into the battery type of behavior. So that's
Pritam,
yes.
Pritam, sorry
Yes.
to disturb you. You have 5 more minutes. Just
Yes,
conclude it.
yes.
Okay.
So see, now what we are looking for, the going into the next type of material. So how we can go, because that are the major challenge. People are just still working on the same materials, And if you want to increase the battery or energy density of the capacitor, you have to work on the materials which are the having the structure similar to the batteries. And that's why we are now proposing the metal organic framework material, because they are the layered materials. See, if you take a lithium cobalt oxide or the LiFeF, they are the interconnected layered materials, but you cannot use them directly as a energy storage devices if you are doing for the higher capacitance, because lithium cannot move that far. However, so people have studied about the ruthenium oxide, MnO2 and all for this one, and most of them are miserably failed, even though they have shown very high potential due to this structural instability. So the framework materials are going to work much beyond that, and they are going to show the light. So see, as you can see that this framework structure have the open pore structure. The ion, especially in terms of the aqueous electrolytes can penetrate them long, and we can get much better density and performance. So we have recently done the work on the CO2O4 nanorods or the cobalt oxalate nanorods. And see what we have done. See, if you take cobalt oxalate, generally you precipitate them in the form of a hydrated material. So this the way they form the framework. But if you do the control heating profile, what we have done at the low temperature water removal, we have converted them into the nanorod type of the structures, and they have performed. See, if you see the black line of the cobalt oxalate hydrated materials to the cobalt oxalate anhydrated materials, there is an enormous increase in the capacity, and now you are seeing the clear intercalative behavior of this CO3 plus 2 plus redox couple, which is very, very active now. And see, these materials have performed of a energy density much higher than the normal capacitors, as well as they perform like a battery. This material itself have an energy density close to 100 milliampere hour per gram. If you see this charge discharge profile, the timeline is 2500 seconds or the 20 minutes what we are charging and discharging at half ampere per gram current rate, and that kind of thing. So, and if you see the detailed electrochemical mechanism, we are seeing this almost 45% of the diffusion control and 65% of the 55% of the capacitive control over the material. So it is ideally a half battery, half capacitor kind of things. And the capacity we are reaching is almost 1269. This one is already known, and our material is showing of the anhydrous nanorods is around 2116 Faraday per gram. And even if we use into Na2C2 Na2SO4 electrolyte, that has going to be a 973 Faraday per gram. So in the aqueous electrolyte, the performance is very high, and when we make the full cell, we are able to reach a power density of the see around just 1 minute 130 watt hour per kg to 90 hour per hour per kg, with the ranging from half ampere per gram to 3 ampere per gram. So ideally we are getting much higher capacity than the normal capacitors, and the energy density are close to the lead acid battery, even better than that, and they are comparable into the energy storage of the lithium-ion batteries. So that's what we have able to achieve.
Please conclude. Please conclude,
Yes.
sir.
So the same way we have developed the another structures, and what we are working on these frameworks, our excavation in that one also resulted in cobalt and nickel oxide mixed structure materials. And now we are going to show you the final results where we are standing in. So these framework materials are generating a power density of 647 watt hour per kg, comparing the with the along with the energy density of the 129 watt hour per kg, and that are the many fold higher than the lead acid batteries energy density and power density. So see, the new materials, especially the structured materials, structural designs can lead us to the grid storage bulk energy devices. So now it's not only that we have made a single electrode test, we have done the full scale test, which is showing very, very promising results, at least for the replacement of the lead acid batteries. So that take up the talk is that, see, the new materials are very important, especially the framework structured materials. Much are better are there to be offered, especially the transition metal oxide, transition metal ion based framework structure that can do the redox, as well as their porosity can give you the very high energy density. So that's all from this talk from my side. So thank you very much for listening me very patiently, because it was a little different escape of the talk from the current talks what have today.
Yeah, I think thank you, Pritam, for giving such a. I could not provide you much better time because we are already running late.
Yes, no problem.
Certainly, your work is very impressive, and we all know Professor good enough. Any solid state ionic society contribution, everything. So I must thank all four speakers for giving me at least opportunity to we work as a session chair and for such a nice, wonderful talk. So I am most thankful to all four speakers along with other audience. And now I am handovering this whole session to none other than Neelamdi. Neelamdi, please.
Thanks, madam.
Yeah.
One party.
The link is different. Link is the same or different? For join. अच्छा, ठीक है.
Thanks.
Thank you.